The oldest mysteries rarely announce themselves. They wait beneath ordinary hills, behind collapsed walls, under streets walked by millions, or inside monuments people thought they already understood. Then something appears, a sealed chamber, an unexpected foundation, a strange alignment, a layer of construction older than everything above it, and the story suddenly changes. Across the ancient world, discoveries like these continue to reveal how incomplete our picture of the past really is. Some overturn ideas held for generations. Others create questions that may take generations to answer. What makes these places extraordinary is not simply their age, but their ability to keep surprising us after thousands of years. Today, we journey into those forgotten corners of history, where one hidden detail can transform everything we thought we knew.
Greenfield Valley, Flintshire, North Wales, is a narrow valley crossed by streams, abandoned mills, and forgotten stone channels. At first glance, it looks like a quiet industrial heritage site. Yet hidden beneath the landscape lies evidence of hydraulic engineering, so precise that some of its methods remain difficult to fully explain today. The valley's historical significance emerged through archaeological investigations, industrial surveys, and restoration projects conducted throughout the 20th century. Researchers uncovered extensive networks of water channels, mill foundations, underground conduits, and mechanical systems that revealed centuries of continuous engineering development. Long before modern power stations existed, water was the primary source of industrial energy. Across Greenfield Valley, generations of builders transformed a natural stream system into a vast hydraulic machine capable of powering mills, workshops, factories, and processing facilities. What makes this remarkable is the level of control they achieved. The valley contains evidence of artificial channels, diversion systems, storage ponds, overflow controls, and water management structures spread across multiple elevations. These systems allowed engineers to regulate water flow with surprising precision. Modern hydraulic engineers understand that even minor errors in gradient can cause serious problems. A channel that is too steep accelerates erosion, while a channel that is too shallow reduces flow velocity and power output. Yet many surviving channels maintain gradients that remain functional centuries after construction. Researchers studying historic water management systems have repeatedly noted that medieval and early industrial builders often achieved remarkable accuracy without modern surveying equipment. Similar examples can be found in Roman aqueducts, which sometimes maintained gradients of only a few centimeters per kilometer. Greenfield Valley appears to belong to that same tradition of practical engineering knowledge. The question is simple. How did builders achieve such precision without lasers, satellites, electronic measuring devices, or modern engineering mathematics? No complete technical manuals survive to provide the answer. Water is both a source of power and an enemy of construction. Much of Greenfield Valley consists of ground exposed to constant moisture, seasonal flooding, and unstable soil conditions. Modern engineers would normally conduct extensive geological surveys before placing heavy structures in such an environment. Yet many historic foundations survived for centuries, and large mills, processing buildings, and industrial facilities operated continuously despite challenging ground conditions. Archaeological investigations have revealed sophisticated foundation techniques involving stone platforms, drainage systems, load distribution strategies, and carefully selected building locations. What remains unclear is how engineers identified stable ground so accurately. There were no geological maps, no drilling rigs, and no computer simulations. Nevertheless, builders repeatedly selected locations capable of supporting massive structures while avoiding many of the unstable areas surrounding them. This pattern is not unique to Greenfield Valley. Similar questions surround medieval cathedrals, Inca mountain fortresses, and numerous ancient engineering projects worldwide. The structures survive, but the calculations behind them often do not. Perhaps the most fascinating engineering puzzle in Greenfield Valley involves the giant water wheels that once powered the valley's industries. Today, water wheels are often viewed as simple machines. In reality, large industrial water wheels were among the most sophisticated mechanical systems of their era. Some 19th century water wheels in Britain exceeded 10 meters in diameter and generated power comparable to dozens of human laborers working simultaneously. A properly designed overshot wheel could achieve efficiencies approaching 70 to 85% under ideal conditions. Remarkably, this is comparable to the efficiency range of many early steam engines. Such performance required extraordinary engineering precision. Every variable mattered, including wheel diameter, bucket geometry, flow rate, water volume, rotational speed, weight distribution, axle alignment, and material strength. Even slight design errors could dramatically reduce performance. Archaeological evidence from Greenfield Valley suggests that engineers developed highly optimized wheel systems capable of powering multiple industrial operations simultaneously. The mystery lies in how they acquired this knowledge. No surviving engineering documents fully explain the design process. No detailed construction blueprints reveal how wheel dimensions were calculated. No records describe how engineers determined the optimal relationship between water volume and rotational speed. Modern reconstructions indicate that successful wheel operation required balancing dozens of interconnected variables. Yet historical builders achieved these results repeatedly. The challenge becomes even greater when considering maintenance. A large water wheel could contain thousands of individual wooden and metal components. Continuous exposure to moisture, changing temperatures, and heavy loads created constant stress on the structure. Despite these challenges, some wheels operated reliably for decades. Experimental archaeologists attempting to recreate historical wheel systems have discovered that apparently simple designs often conceal extremely sophisticated engineering principles. Fluid dynamics, momentum transfer, structural mechanics, and energy optimization all played critical roles. Many of these principles were understood through experience rather than formal scientific theory. The builders knew what worked, but what remains uncertain is how they learned it. Beneath the visible landscape lies another mystery. Archaeological surveys have identified sections of underground channels, drainage tunnels, culverts, and concealed water management systems running beneath parts of the valley. Some were designed to prevent flooding, others redirected water toward industrial facilities, and some may have served multiple purposes simultaneously. Many of these structures remain only partially understood. Several were modified repeatedly over centuries, making it difficult to determine their original design. What impresses engineers today is their effectiveness. Even after decades or centuries of use, many systems continue to manage water flow successfully. This raises important questions. How are these tunnels surveyed underground? How are gradients maintained without modern instruments? How are structural failures prevented? The answers remain incomplete. Near the valley stand the remains of Basingwerk Abbey, a Cistercian monastery founded during the 12th century. The Cistercians were among the most technologically advanced monastic orders in medieval Europe. Across the continent, they became famous for their expertise in water management, milling technology, metallurgy, and agricultural engineering. Many historians suspect that at least part of Greenfield Valley's hydraulic tradition may trace its origins to knowledge developed or preserved by these monks. The problem is evidence. Large portions of medieval documentation have disappeared, construction records are incomplete, and technical instructions rarely survived. As a result, historians cannot fully reconstruct how knowledge moved from monastic communities into later industrial systems. This creates a fascinating possibility. Some engineering techniques used in the valley may represent centuries of accumulated expertise whose origins have been largely forgotten. Another mystery concerns resource extraction. For centuries, local industries exploited stone, clay, minerals, and other natural resources found throughout the region. Many extraction sites were located in geologically favorable areas. Today, identifying such locations often requires detailed surveys, geological mapping, laboratory analysis, and remote sensing technologies. Historical work has had none of these tools, yet they repeatedly discovered productive deposits. Researchers suspect that generations of observation allowed workers to recognize subtle environmental clues invisible to most people. These clues may have included variations in vegetation, changes in soil coloration, water chemistry, rock exposures, and drainage patterns. Individually, these indicators may seem insignificant. Together, they may have formed a practical geological science developed through centuries of experience. The full extent of that knowledge remains unknown. What do you think? Were the engineers of Greenfield Valley simply masters of observation and experience, or did they possess practical engineering knowledge far more advanced than history has given them credit for? Let us know your thoughts in the comments below. Inside the ruins of Praia Palile, massive trees crush ancient stone walls that should have collapsed centuries ago, yet the temple still stands. Built on unstable tropical soil nearly 800 years ago, surrounded by humidity, floods, roots, and erosion, Praia Palile survives in conditions that destroy most stone structures within a fraction of that time. Archaeologists studying the site discovered something disturbing. Many of its engineering solutions resemble concepts used in modern structural stabilization, and nobody fully understands how the Khmer Empire achieved them without advanced machinery, modern surveying tools, or reinforced concrete. Unlike Angkor Wat, Praia Palile remained largely isolated for centuries beneath dense Cambodian jungle growth inside Angkor Thom. French explorers and archaeologists working for the École Française d'Extrême Orient documented the temple during the late 19th and early 20th centuries as they began clearing large sections of Angkor. What they found was not a massive ceremonial complex, but a strangely quiet temple with unusual structural features, steep stairways, hybrid religious iconography, and foundations that appeared far more sophisticated than expected for the period. The greatest engineering mystery surrounding Praia Palile is not the visible temple itself, but what lies underneath it. The entire Angkor region sits on highly unstable tropical ground, affected by monsoon cycles, seasonal flooding, shifting groundwater, and compressible sediment layers. Modern engineers consider this type of environment extremely difficult for heavy masonry construction. Even today, buildings constructed on weak saturated soil often require deep reinforced foundations, concrete piles, or soil stabilization systems to prevent uneven settlement. Yet the Khmer Empire built enormous stone monuments here nearly a millennium ago. Geological studies across Angkor have shown that Khmer builders frequently used layered laterite, compacted sand and sandstone blocks arranged in carefully engineered sequences beneath temple platforms. At Praia Palile, this foundation system appears unusually effective. Despite centuries of root invasion and structural stress, major sections of the temple remain standing. What makes this so mysterious is the apparent understanding of load distribution. Some structural engineers comparing Angkorian construction techniques to modern concepts have suggested that Khmer builders unintentionally developed primitive forms of floating foundation systems. Instead of forcing structures onto rigid, deep supports, they created wide, stabilized platforms that distributed weight across soft terrain. This approach resembles principles now used in modern geotechnical engineering. The comparison becomes even more striking when examining environmental pressure. Cambodia's tropical climate receives roughly 1,500 to 2,000 millimeters of rainfall annually. Tree roots in jungle environments generate enormous mechanical force over time. Certain tropical species can split concrete, asphalt, and modern retaining walls within decades. Yet parts of Praia Palele survived centuries of direct root compression. Some sandstone blocks remain aligned despite trees physically growing through the structure. This creates one of the biggest unanswered questions in Khmer engineering. How did builders without modern geology understand how to prevent catastrophic foundation collapse in one of the most destructive construction environments on Earth? The stairways at Praia Palele are unusually steep, even compared to other Khmer temples. Certain sections approach angles that modern public safety standards would consider impractical or dangerous. The common explanation is symbolic. The ascent represented movement from the human world toward the divine realm. But symbolism alone does not explain the engineering challenge. Constructing extremely steep stone staircases in tropical conditions is structurally risky. Water erosion rapidly weakens exposed edges. Weight concentration increases stress fractures. Small design errors can destabilize entire stair sections over time. Yet many of Praia Palele's stairways retain recognizable geometry after centuries of weathering. Researchers comparing Angkorian architecture with Mesoamerican pyramids have noted surprising similarities in elevation symbolism and steep ceremonial ascent. However, there is no evidence of contact between the civilizations. The resemblance may instead suggest that ancient societies independently discovered similar architectural solutions for monumentality and religious psychology. Still, the precision required to maintain balance and symmetry on such steep inclines without modern mathematical instruments remains difficult to explain fully. Several stone joints at Praia Palele display extremely tight fitting between sandstone blocks. In certain areas, gaps are thin enough that even modern blades struggle to pass through them. This is one of the most controversial recurring mysteries in ancient architecture worldwide. Similar precision appears in Inca masonry at Sacsayhuaman in Peru, granite construction at Giza in Egypt, polygonal stonework at Ollantaytambo, and certain Roman imperial structures. The Khmer Empire primarily relied on iron tools, manual labor, and basic lifting systems. Yet sandstone surfaces at Praia Palele often appear flattened and aligned with remarkable consistency. Modern stoneworkers note that high-precision fitting usually requires repeated surface grinding, accurate measuring systems, controlled cutting angles, and stable transport methods. But Khmer builders operated inside dense tropical forests under extreme humidity and heat. Even more puzzling is transportation. Some sandstone blocks used throughout Angkor weigh multiple tons and originated from quarries near Phnom Kulen, over 50 kilometers away. Transport likely relied on canals, rafts, elephants, rollers, and manpower. However, no definitive reconstruction fully explains how such large-scale logistical precision was consistently maintained across the empire. Praia Palele contains signs of multiple religious transitions layered directly into its structure. Earlier Khmer architecture was heavily influenced by Hindu cosmology, especially Shaivism and Vishnu worship. Later phases of Angkor shifted increasingly towards Mahayana Buddhism and eventually Theravada Buddhism. At Praia Palele, these transitions appear physically embedded into the temple itself. Some carvings reflect classical Hindu iconography, while others contain Buddhist imagery associated with later centuries. The result is a structure that looks almost architecturally divided across time. Normally, temples rebuilt centuries apart reveal obvious inconsistencies in engineering and alignment. But several sections at Praia Palele connect with surprising structural continuity. This suggests one of two possibilities. Either Khmer engineers preserved highly standardized construction knowledge for generations, or their architectural systems were far more mathematically organized than historians once believed. Perhaps the strangest mystery is not how the temple was built, but why it still exists. Tropical environments are devastating for sandstone. High humidity accelerates chemical weathering. Biological organisms penetrate porous surfaces. Constant rainfall weakens mineral bonds. Modern conservationists at Angkor continuously battle deterioration. Yet, some carvings at Preah Palelai remain visible after centuries of exposure. Microscopic analysis of Angkorian sandstone has revealed variable resistance depending on mineral composition, porosity, and grain bonding. Certain blocks appear significantly more resistant to erosion than expected. This has led to theories that Khmer builders may have intentionally selected sandstone with unusually durable mineral structures. Others speculate they possess surface treatment methods now lost to history. No definitive answer exists. What is clear is that many surviving Khmer structures continue outperforming what modern researchers initially predicted they should survive. What do you think the Khmer Empire truly understood about engineering and construction that may have been lost to history? Share your thoughts in the comments below. The eastern coast of Anglesey, Wales, overlooking the narrow waters of the Menai Strait, is home to the ruins of Castell Aberlleiniog, a site that conceals a mystery far greater than a medieval fortress. Beneath its earthworks lies evidence of engineering knowledge that historians still struggle to fully explain. Located near the town of Beaumaris on the Isle of Anglesey, Castell Aberlleiniog was first documented in medieval records dating to the Norman expansion into Wales during the late 11th and early 12th centuries. Archaeological excavations and modern LiDAR surveys have since revealed far more extensive defensive systems than previously believed. At first glance, Castell Aberlleiniog appears to violate one of the most basic principles of medieval military architecture. Most Norman castles were constructed on high ground because elevation provided superior visibility, greater defensive advantages, and natural protection against attack. Famous examples such as Dover Castle, Bamborough Castle, and numerous Welsh fortresses all exploited elevated terrain. Yet Castell Aberlleiniog sits relatively close to sea level near coastal wetlands. Why would experienced Norman military engineers choose such a location? The answer remains unclear. Modern terrain analysis suggests the builders may have prioritized control of transportation routes rather than purely defensive advantages. The castle occupies a strategic position overlooking approaches between Anglesey and mainland Wales through the Menai Strait, one of the most important waterways in the region. Computer-based visibility studies indicate that observers stationed within the fortress could monitor both maritime and inland movement across a surprisingly large area. In effect, the location functioned less like an isolated stronghold and more like a surveillance platform controlling regional movement. What remains unexplained is how Norman engineers identified this optimal location without modern mapping technology, aerial surveys, satellite imagery, or advanced geographic measurements. Their decision appears remarkably sophisticated even by modern military planning standards. The most impressive surviving feature of Castell Aberlleiniog is not a tower or stone wall, it is the earth itself. Large defensive ditches and embankments still surround the site, and archaeologists estimate that thousands of cubic meters of soil were excavated and relocated during construction. For a relatively modest fortress, the scale of the earthworks appears unusually large. This raises a significant question. Why invest such extraordinary labor into moving vast quantities of earth when many Norman castles relied primarily on timber fortifications? Recent studies of medieval fortifications suggest that earthworks provided advantages often underestimated by modern observers. Massive embankments absorbed impacts more effectively than stone walls against certain siege technologies, while deep ditches forced attackers into predictable paths, creating deadly defensive kill zones. Computer simulations performed on similar Norman fortifications demonstrate that carefully designed earthworks could increase defensive efficiency dramatically, allowing smaller garrisons to resist larger attacking forces. Yet no surviving engineering documents explain how medieval builders calculated ditch depths, embankment angles, or defensive geometries. The earthworks of Castel Aberlleiniog may preserve practical military mathematics that disappeared centuries ago. Water has always been one of the most important elements in military engineering. A fortress with too much water becomes unstable, while a fortress with too little loses valuable defensive advantages. Castel Aberlleiniog presents a fascinating puzzle because it was constructed near wetlands, coastal zones, and fluctuating groundwater conditions. Excavations have identified possible drainage channels beneath portions of the defensive earthworks, suggesting deliberate attempts to manage water movement throughout the site. The sophistication of the system remains debated. Some researchers believe the builders possessed an advanced practical understanding of local hydrology, developed through generations of observation, while others argue that the drainage network may represent later modifications. What makes the mystery particularly intriguing is that similar hydraulic solutions appear in medieval castles hundreds of kilometers apart. Sites such as Caerphilly Castle and several Norman fortifications in England demonstrate surprisingly effective water management systems despite being constructed long before the development of modern engineering science. The question remains unanswered: how did medieval builders consistently manipulate groundwater and surface water without geological surveys, computer modelling, or modern hydraulic calculations? Of all the engineering puzzles surrounding Castel Aberlleiniog, none may be more fascinating than its foundations. This mystery lies beneath the visible ruins. The castle was not constructed on solid mountain bedrock. Instead, significant portions of the site occupy relatively soft coastal ground, influenced by moisture, sediment movement, and long-term environmental change. From an engineering perspective, this should have been a major problem. Modern construction on weak soil often requires deep foundations, reinforced concrete piles, geotechnical analysis, and extensive drainage systems. Without such measures, structures can sink, tilt, crack, or collapse. Yet Castel Aberlleiniog survived for centuries. Archaeological investigations suggest that the builders may have employed layered foundation systems composed of compacted earth, gravel, stone fragments, and carefully selected fill materials. This approach bears remarkable similarities to principles used in modern geotechnical engineering. Today, engineers improve weak ground by distributing loads across wider surfaces, increasing drainage capacity, reducing water retention, and minimizing uneven settlement. Evidence from Castel Aberlleiniog suggests medieval builders may have achieved comparable results using entirely empirical methods. The challenge is that no construction manuals survive. No drawings explain how the ground was prepared. No records describe how materials were selected, and no documents reveal how settlement was monitored. What astonishes modern researchers is that many foundation failures in contemporary construction occurred despite sophisticated engineering software. Yet, medieval builders working without mathematics as we know it managed to create structures that remained stable for generations. This mystery is not unique to Castel Aberlleiniog. Similar questions surround the foundations of Venice, where millions of wooden piles support entire districts. They also appear at Mont Saint-Michel in France and numerous medieval waterfront fortifications throughout Europe. In every case, builders demonstrated an ability to understand soil behavior long before geotechnical engineering existed as a scientific discipline. The fortress may therefore preserve evidence of a forgotten engineering tradition based entirely on observation, experimentation, and accumulated practical knowledge. The castle's position offers visibility toward multiple strategic locations around the Menai Strait. This has led some historians to propose that Castel Aberlleiniog may have been part of a larger signalling network. Throughout medieval Europe, warning systems frequently relied on fire beacons, smoke signals, and visual communication stations positioned across long distances. Under favourable conditions, such systems could transmit warnings dramatically faster than horseback messengers. The problem is that physical evidence rarely survives. Wooden beacon towers disappear, signal platforms erode, and documents are lost. As a result, researchers can only reconstruct fragments of these communication systems. If Castel Aberlleiniog participated in such a network, it may have functioned as an important information hub, controlling maritime traffic and military intelligence across northern Wales. The technological organisation required for such a system remains poorly understood. One reason Castel Aberlleiniog remains mysterious is that much of the original fortress was built from timber rather than stone. Wood rarely survives for centuries in exposed environments. As a result, the visible ruins represent only a fraction of the original complex. Excavations have revealed post holes indicating substantial wooden buildings, towers, defensive walls, and internal structures. These discoveries suggest a much larger and more sophisticated fortress than earlier historians imagined. Yet reconstruction remains difficult. Researchers know where some structures stood, but they cannot fully determine their height, load-bearing systems, construction methods, or architectural details. The result is a castle that remains partially invisible. Its surviving earthworks preserve the footprint of lost engineering, while the structures themselves have disappeared almost entirely. What do you think? Were the engineers of Castel Aberlleiniog simply masters of experience and observation? Or did they possess technical knowledge far more advanced than history has given them credit for? Let us know your thoughts in the comments below. Rows of stone rise silently from the Sardinian earth, stretching across a landscape that feels too ordered to be natural, yet too ancient to be understood. And at first glance it looks like a cemetery, but the longer you observe it, the less it behaves like one, because cemeteries do not normally require dozens of standing stones aligned across open terrain, forming patterns that seem to follow rules no one can fully decode. And yet here at Pranu Mutadu, that is exactly what we find, a burial ground that looks disturbingly like a system, a place where intention is visible but meaning is missing, and where every stone seems to belong to a design that no longer speaks its original language. Located near the modern town of Goni in Sardinia, Pranu Mutadu was not uncovered in a single dramatic moment, like many famous archaeological discoveries, but instead revealed itself slowly through decades of systematic surveys and excavations conducted throughout the 20th century, where what initially appeared to be scattered stones embedded in the landscape gradually emerged as a structured archaeological complex. As researchers identified more than 60 menhirs, many standing between 1 and 3 meters tall, alongside multiple dolmens constructed from massive stone slabs, forming burial chambers that date back to approximately 4000 to 3000 BCE within the Neolithic period, and at this early stage the interpretation appeared straightforward, a prehistoric necropolis. Yet as excavations expanded and mapping techniques improved, a critical inconsistency began to emerge, because the stones were not randomly placed as one would expect in a simple burial field, but instead followed patterns, orientations, and spatial relationships that suggested deliberate organization. With each new excavation phase, the site became increasingly complex and difficult to categorize, as early investigations focused on funerary structures, where dolmens revealed fragmented human remains, basic grave goods including pottery fragments and stone tools, and clear signs of repeated use across generations, indicating that the site functioned as a burial ground over an extended period of time. Yet as archaeologists expanded their surveys and began to analyze the spatial distribution of the menhirs, a more structured pattern started to appear, because these standing stones were not merely marking individual graves, but instead formed long linear alignments stretching across the terrain, some extending for dozens of meters, while others created clustered formations that hinted at geometric planning. And in certain areas the stones appeared to maintain consistent directional orientation, which could not easily be explained by terrain or convenience. And by the late 20th century, this accumulation of evidence forced researchers to reconsider the entire nature of the site, leading to the realization that Pranu Mutedu was not simply a cemetery, but a designed landscape with rules that remain only partially understood. The people responsible for constructing Pranu Mutedu lived in a time before metal tools, before written language, and before formalized systems of mathematics. And yet they achieved a level of organization that appears strikingly advanced for its context, as they were able to quarry and transport stones weighing hundreds of kilograms, sometimes approaching 1 or 2 metric tons, move them across uneven terrain without the aid of wheeled transport, and erect them vertically with sufficient stability to withstand erosion, weathering, and the passage of thousands of years. And more importantly, they arranged these stones across distances in ways that strongly suggest intentional spatial planning, because placing a single menhir upright requires knowledge of leverage, balance, and soil stability. But aligning dozens of them in consistent orientations implies something more systematic, possibly a method of measurement using ropes, pacing systems, or visual sightlines, creating a paradox that appears repeatedly in prehistoric archaeology, where the technological simplicity of the tools stands in contrast with the complexity and precision of the final result, producing outcomes that feel less accidental and more engineered. Among all the unresolved aspects of Pranu Mutedu, the question of astronomical alignment remains one of the most debated and scientifically intriguing, as preliminary observations suggest that many of the stone rows follow a general east-west orientation, aligning broadly with the path of the sun as it rises and sets, a directional pattern that held symbolic and practical importance in numerous ancient cultures, often representing cycles of life, death, and renewal. Yet the consistency observed across multiple alignments suggests that this may extend beyond symbolic placement, and when compared with other prehistoric sites, the implications become even more significant. Because at Stonehenge, the primary axis aligns with remarkable precision to the summer solstice sunrise, an event that occurs only once each year, while at Carnac stones in France, more than 3,000 standing stones are arranged in long, parallel rows that some researchers believe may correspond to lunar or solar cycles. And although Pranu Mutedu does not exhibit the same degree of precision, the repeated directional consistency suggests that its builders may have been responding to similar observational patterns. Yet the lack of exact calibration introduces ambiguity, because the alignments are too structured to be dismissed as random, but not precise enough to confirm the existence of a fully developed astronomical observatory, leaving open the possibility that the builders were engaging in observational practices that were empirical rather than mathematical, or, alternatively, that they were replicating inherited traditions whose original purpose was only partially understood, raising the possibility that the site represents not a single coherent system, but the accumulation of knowledge passed down and gradually transformed over generations. The presence of dolmens confirms that Pranu Mutedu functioned at least in part as a burial ground, but the scale, organization, and integration of the menhirs suggest that its purpose extended beyond simple interment, indicating that the site may have served multiple overlapping roles, including a space for communal rituals, seasonal gatherings, and possibly symbolic interactions with cosmological ideas, because in many prehistoric belief systems, death was not viewed as a final endpoint, but rather as a transition within a larger cosmic cycle, and aligning the dead with the movement of the sun or other celestial phenomena may have represented an attempt to integrate human existence into the broader structure of the universe, suggesting that the site functioned not only as a resting place for the dead, but also as a stage for the living to engage with concepts of time, continuity, and existence, where ritual, observation, and memory intersected within a carefully structured environment. Radiocarbon dating and stratigraphic analysis indicate that Pranumutadu was not constructed in a single unified phase, but instead developed gradually over centuries, with evidence suggesting continuous or repeated use from the early Neolithic onward, introducing a significant layer of complexity, because it implies that multiple generations contributed to the formation of the site, potentially modifying, expanding, or reinterpreting its original layout. And this pattern is consistent with what has been observed at sites like Göbekli Tepe, where later communities interacted with monumental structures that may have already lost their original meaning. And if a similar process occurred at Pranumutadu, then some of the alignments and structures present today may represent a form of inherited knowledge, preserved through repetition but gradually detached from its initial purpose, resulting in a system that continued to exist even as its underlying logic became increasingly obscure. Today, Pranumutadu remains partially understood but fundamentally unresolved, as modern archaeological methods allow researchers to map the site with high precision, analyze soil composition, date organic materials, and reconstruct aspects of its use. Yet these tools have not been able to fully explain why the site was constructed in the way it was, because the evidence points simultaneously toward burial practices, ritual activity, and spatial organization, without providing a single unifying explanation that accounts for all observed features, leaving behind a structured mystery in which intention is evident but interpretation remains incomplete, a place where patterns are visible but their meaning continues to resist translation. Do you think Pranumutadu is just a simple burial ground, or a system we still don't fully understand? Let me know your thoughts in the comments below. A grassy depression on the edge of Caerleon, Wales, attracted antiquarian attention for centuries before systematic archaeological excavations in the 19th and 20th centuries revealed its true identity as one of the best preserved Roman military amphitheatres in Britain. Built around AD 90 beside the fortress of the Second Augustan Legion, the structure could hold approximately 6,000 spectators. At first glance, it appears to be simply another Roman arena, yet beneath its grassy banks lies a collection of engineering mysteries that continue to challenge archaeologists, architects, and historians. Nearly 2,000 years after its construction, researchers still debate how Roman engineers achieved such remarkable performance in acoustics, drainage, earthwork stability, logistics, and large-scale construction without leaving behind detailed technical manuals. The first mystery begins with the amphitheatre's location itself. Wales is not the sort of environment where large earthworks should survive easily for nearly 2 millennia. The region receives significant rainfall throughout the year, creating conditions that encourage erosion, waterlogging, and structural instability. Modern civil engineers understand that large earthen embankments require careful calculations involving soil density, moisture content, drainage gradients, and load distribution. Yet Roman engineers constructed enormous seating banks capable of supporting thousands of people while maintaining stability for centuries. Archaeological studies indicate that the seating areas were created using carefully layered earth and rubble deposits, compacted in stages. What remains unclear is exactly how Roman builders determined the correct mixture of materials and compaction techniques. No surviving Roman document explains the engineering procedures used at Caerleon. The structure simply exists as evidence that the knowledge once existed. The scale of the earthworks becomes even more impressive when compared with other ancient construction projects. The amphitheatre measures approximately 86 metres by 73 metres, making it one of the largest Roman arenas in Britain. Moving and compacting the enormous volume of soil required would have demanded a highly organised workforce. Modern estimates suggest that thousands of cubic metres of material were transported, positioned, and compacted during construction. Unlike modern builders, Roman engineers had no bulldozers, excavators, or hydraulic compactors, yet they successfully created embankments that have survived longer than many 19th century engineering projects. The question is not whether they possessed the necessary knowledge. The question is how they acquired it and why so little documentation survives. Another mystery concerns the amphitheatre's remarkable acoustics. Roman architects repeatedly demonstrated an ability to create venues where speech could travel surprising distances. Similar effects can be observed in structures such as the Roman theatre's Orange in France and Aspendos in Turkey. Caerleon presents a particularly interesting case because much of the original stone seating has disappeared, leaving primarily the earthworks behind. Nevertheless, studies of the arena's geometry suggest that the elliptical design helped concentrate and distribute sound efficiently. A person standing near the centre could potentially be heard by spectators seated around the arena without any amplification technology. Modern acoustic engineers can model such effects using sophisticated computer simulations, yet Roman builders achieved them through practical experience and empirical design. Whether they fully understood the underlying physics remains unknown. The drainage system represents another engineering puzzle. Rainfall has always posed a major threat to open-air arenas. Without effective drainage, the central arena would quickly become unusable. Excavations have revealed evidence of underground drains and water management features beneath the amphitheatre. Some sections continue to function surprisingly well despite their age. Roman engineers throughout the empire displayed exceptional expertise in hydraulic engineering. Their aqueducts carried water across vast distances with gradients often measured in only a few centimetres per kilometre. At Caerleon, however, the challenge was the opposite. Instead of transporting water in, they needed to remove it efficiently from a rain-soaked environment. Archaeologists still do not possess a complete map of the original drainage network. Portions remained buried, damaged, or lost entirely. The surviving evidence demonstrates sophisticated planning, but leaves many questions unanswered regarding the full design. Perhaps even more fascinating is the relationship between the amphitheatre and the military fortress it served. Caerleon was not merely a civilian settlement, it was one of the most important Roman military bases in Britain, housing thousands of legionaries. The amphitheatre stood outside the fortress walls, yet remained closely connected to military life. Historians traditionally interpret the structure as a venue for training exercises, public ceremonies, entertainment, and displays of military skill. However, certain architectural features suggest that its role may have been more complex. Subterranean passages and service corridors indicate a carefully organized movement system beneath the arena. These spaces allowed participants, animals, equipment, and performers to enter and exit efficiently. Yet archaeologists continue to debate whether all of these underground areas have been identified. Geophysical surveys have detected anomalies beneath the site that may indicate additional buried structures still awaiting excavation. The mystery deepens when considering the speed at which Roman construction projects could be completed. Building an amphitheatre capable of holding 6,000 spectators required surveying, excavation, earth-moving drainage installation, structural reinforcement, and architectural planning. Modern project managers understand the complexity of coordinating such operations. Roman engineers achieved similar results repeatedly across Europe, North Africa, and the Middle East. The Colosseum in Rome, capable of holding tens of thousands of spectators, was completed in less than a decade. Although Caerleon was much smaller, the same organizational principles appear to have been at work. The empire's ability to mobilize labor, materials, and expertise remains one of the great logistical achievements of the ancient world. Yet the administrative systems that made such efficiency possible are only partially understood. Excavations have also revealed evidence suggesting that the amphitheatre visible today represents only a fraction of the original complex. Archaeological investigations conducted over many decades uncovered entrances retaining structures and internal features that had been hidden beneath accumulated soil. More recent geophysical surveys have identified additional subsurface anomalies. Ground-penetrating radar and magnetometry can detect buried structures without excavation, and several unexplained features remain under investigation. Some researchers suspect that associated buildings once surrounded the arena, serving administrative, military, or ceremonial functions. Others argue that certain anomalies may simply reflect later modifications. Until further excavations occur, these questions remain unresolved. The survival of the amphitheatre also raises questions about Roman material science. Ancient builders selected specific combinations of soil, stone, timber, and drainage materials capable of enduring centuries of environmental stress. Similar mysteries surround Roman concrete, whose durability continues to attract scientific attention. Studies published in recent years have shown that Roman concrete sometimes developed self-healing properties through chemical reactions involving lime clasts and water infiltration. Although Caerleon relies more heavily on earthworks than concrete, the same broader principle applies. Roman engineers repeatedly produce structures whose longevity exceeds expectations. Their success suggests a practical understanding of materials that modern researchers are still attempting to reconstruct. The amphitheatre's role in Roman Britain introduces another layer of mystery. Historical records concerning the site are limited. Archaeological evidence provides valuable clues, yet many details of daily operations remain uncertain. How frequently were events held? What kinds of spectacles took place? How were large crowds managed? How were performers and animals transported through the underground passages? The physical structure provides partial answers, but the complete picture remains elusive. Every excavation uncovers new information while simultaneously revealing new gaps in our understanding. Buried beneath the soils of central Ukraine lies evidence of a building so large, so organized, and so deliberately constructed that it challenges one of the most fundamental assumptions in archaeology: that complex, large-scale architecture requires complex, hierarchical societies. At a time when most human communities were expected to live in small, scattered villages, Nebelivka reveals something entirely different: a coordinated, planned settlement stretching across more than 250 hectares, with a central structure that many researchers now describe as a temple. But the deeper archaeologists dig, the more unsettling the pattern becomes. This was not just built, it was burned. And the question is not how it was destroyed, but why it was designed to be destroyed at all. The story begins not with excavation, but with anomalies detected from above. In the early 21st century, aerial surveys and geophysical scans revealed faint circular patterns beneath agricultural fields near the village of Nebelivka. What initially appeared to be irregular soil marks soon resolved into something far more structured: concentric rings of dwellings, radial pathways, and a dense, organized layout extending over roughly 260 hectares. This site belonged to the Tripilia culture, a Neolithic society dated to approximately 4000 to 3500 BCE. Based on settlement density, researchers estimated a population between 10,000 and 15,000 individuals. For comparison, this places Nebelivka on a scale comparable to early Uruk, widely considered one of the world's first true cities. Yet Uruk flourished nearly a millennium later. The implication was immediate and controversial. Either Nebelivka represented an early form of urbanism far ahead of its time, or our definition of what constitutes a city was fundamentally incomplete. Initial excavations focused on anomalies detected near the center of the settlement. What archaeologists uncovered was not a typical dwelling, but a massive rectangular building measuring approximately 60 meters in length and 20 meters in width, covering more than 1,000 square meters. Evidence suggested that the structure may have been 2 stories high, an extraordinary architectural feat for a Neolithic society relying on wood and clay. Inside, researchers identified multiple rooms with distinct functions: raised platforms interpreted as altars, fragments of clay figurines, storage features, and carefully organized interior divisions. The absence of domestic debris such as cooking waste or everyday tools indicated that this was not a residential building. At this stage, comparisons became unavoidable. Sites such as Çatalhöyük, dating to a similar period, display dense habitation but lack centralized monumental structures of this scale. Nebelivka, by contrast, appeared to possess a focal building that required coordinated labor, planning, and symbolic intent. The term temple began to circulate not as a definitive classification, but as a working hypothesis. Subsequent field seasons expanded the excavation area and integrated high-resolution magnetometry data. The settlement's layout became increasingly clear. Thousands of structures arranged in concentric rings, intersected by radial pathways, with open spaces that may have functioned as communal zones. This level of spatial organization suggests intentional planning rather than organic growth. In contrast, many early settlements evolved incrementally, producing irregular layouts shaped by terrain and social clustering. Nebelivka, however, exhibits geometric consistency across a vast area. The central megastructure occupies a strategic position within this layout, reinforcing its importance. Yet no evidence of fortifications, administrative buildings, or elite residences has been identified. This absence raises a critical contradiction. The site demonstrates large-scale coordination, but lacks the hierarchical markers typically associated with such organization. Was Nebelivka governed by an unseen authority, or does it represent a fundamentally different model of social cooperation? One of the most striking discoveries emerged from the analysis of structural remains. The central building and many surrounding structures had been subjected to intense burning. The temperatures reached were sufficient to transform clay surfaces into hardened, ceramic-like material. Crucially, the burn patterns do not align with accidental fire. Instead, they suggest controlled, deliberate ignition. The distribution of heat, the uniformity of damage, and the lack of chaotic collapse all point toward a coordinated event. This phenomenon is not unique to Nebelivka. Other Tripilia sites exhibit similar evidence of burning. However, the scale observed here is unprecedented. entire sections of the settlement appear to have been intentionally destroyed. Several hypotheses have been proposed. One suggests ritual renewal, in which structures were periodically burned and rebuilt as part of a cyclical belief system. Another interprets the burning as a form of social or symbolic closure, an intentional erasure marking the end of occupation. Yet no consensus has been reached. What remains is a pattern that defies conventional explanations, a society investing enormous effort into construction, only to systematically dismantle its own achievements. At first glance, the construction techniques at Nebelivka appear straightforward. Buildings were constructed using timber frameworks coated with layers of clay, a method consistent with Neolithic architecture across Europe. No metal tools, no advanced engineering systems, and no evidence of specialized materials have been identified. However, the outcome tells a different story. When subjected to high temperatures during the burning phase, the clay coatings underwent a transformation. They hardened into a durable, brick-like substance, significantly increasing structural stability and longevity. In some cases, these materials exhibit properties comparable to early fired bricks, which are typically associated with later civilizations in Mesopotamia. Experimental archaeology has attempted to replicate this process by constructing similar timber and clay structures and burning them under controlled conditions. Researchers have demonstrated that such transformations are possible, but only within specific temperature ranges and burn durations. Achieving consistent results would require either precise control or repeated experience. This raises a critical question. Was this effect intentional or accidental? If intentional, it implies that the builders of Nebelivka possessed an empirical understanding of material transformation, recognizing that controlled burning could enhance durability. If accidental, it suggests that a byproduct of ritual destruction inadvertently produced a superior construction material. In either case, the result is the same: a simple technology producing outcomes that appear disproportionately advanced. When compared to early Mesopotamian brick production, which involved deliberate kiln firing and standardized molds, Nebelivka represents a parallel pathway less formalized, yet functionally effective. This challenges the linear model of technological development, in which innovations are assumed to emerge in a single region and diffuse outward. Instead, Nebelivka suggests that complex material knowledge may have arisen independently in forms that are difficult to recognize within traditional frameworks. The evidence converges on a series of unresolved questions. First, the nature of the settlement itself. Is Nebelivka a true city, predating urbanism as defined by Mesopotamian models, or is it a large aggregation of seasonal populations, an intermittent gathering place rather than a permanent habitation? Second, the function of the central megastructure. While ritual activity is strongly indicated, the scale and complexity of the building exceed what is typically associated with purely ceremonial spaces in Neolithic contexts. Could it have served multiple roles, religious, social, and administrative, within a society that left no written records? Third, the meaning of the burning events. If these were ritual acts, what belief system required the destruction of such significant investments? If they were practical, what purpose did they serve in the life cycle of the settlement? Each question points to a deeper issue: the possibility that our current models of early human societies are too narrow to accommodate the variability observed in the archaeological record. Scholars remain divided. Some argue that Nebelivka represents a form of low-density urbanism, where large-scale coordination was achieved without centralized authority. Others suggest it was only a periodic gathering site, making its size appear more like a city than it actually was. The central structure is also debated. It may have been a temple, but it is equally possible that modern interpretations are being projected onto a prehistoric context. Without written records, all conclusions rely on material evidence, and that evidence allows for multiple interpretations. What is clear is that Nebelivka does not fit any existing model. It exists somewhere between a village and a city, between ritual and infrastructure, and between simplicity and a level of complexity that remains difficult to explain. If Nebelivka was not a city in the way we understand cities, then what exactly was it? And how many other cities in history have we completely misunderstood? Perched high above the town of Llangollen in northern Wales, Castell Dinas Bran is one of Britain's most enigmatic hilltop fortresses. Rising approximately 321 metres above sea level, the ruins visible today were constructed during the 13th century by the Welsh prince Gruffydd Maelor II. Archaeologists first began systematic investigations during the 19th century, yet nearly 2 centuries of research have failed to answer some of the site's most intriguing questions. Beneath the ruined walls lies evidence of engineering, surveying, logistics, and landscape management that remains only partially understood. What appears at first glance to be a simple medieval castle may in fact preserve traces of much older traditions and technological knowledge whose details have largely vanished. The first mystery concerns the hill itself. Dinas Bran occupies what many military historians consider an almost perfect defensive position. Modern topographic analysis shows that the summit commands views across the Dee Valley for many kilometers in multiple directions. Any movement through the valley would have been visible long before attackers approached the fortress. What makes this remarkable is the precision with which the location was selected. Medieval builders possessed no satellite imagery, aerial photography, GPS systems, or modern geographic and information software. Yet they chose a summit that maximized visibility while minimizing vulnerabilities. Similar strategic placement can be observed at sites such as Maiden Castle and Dunnottar Castle, but Dinas Bran achieves this advantage on an exceptionally isolated peak. Researchers still debate whether this positioning resulted from generations of accumulated local knowledge or from surveying techniques more sophisticated than surviving records suggest. An even greater mystery involves construction logistics. The castle stands atop a steep limestone hill where gradients in some areas exceed 30 degrees. Every block of stone, every timber beam, every tool, and every supply item had to be transported hundreds of meters uphill. Modern estimates suggest that several thousand tons of building material were required during construction. Without motorized transport, cranes, or modern lifting equipment, the builders somehow moved these materials to one of the most inaccessible construction sites in medieval Wales. Archaeologists have proposed ramps, sledges, wooden rollers, animal traction, and pulley systems. Yet no definitive evidence survives to confirm which method was actually employed. Similar questions surround the transport of stone at sites such as Machu Picchu and Sacsayhuaman, where enormous logistical achievements remain difficult to reconstruct. Dinas Bran may not involve stones weighing hundreds of tons, but the challenge of moving thousands of smaller blocks to such an extreme elevation remains impressive even by modern standards. The geology of the site introduces another puzzle. The castle sits upon limestone formations that have remained remarkably stable despite centuries of exposure to wind, rain, frost, and erosion. Modern geotechnical engineers carefully evaluate load-bearing capacity before constructing on elevated terrain, yet medieval builders possessed no formal geological science. Somehow they selected foundation points capable of supporting substantial defensive structures for centuries. The surviving ruins demonstrate that the builders understood which areas of bedrock could safely support walls and towers. Whether this knowledge came from observation, empirical testing, inherited traditions, or some combination of all three remains unknown. Similar mysteries exist at sites like Meteora, where builders established structures atop seemingly impossible rock formations long before modern engineering principles were formalized. One of the most debated questions concerns what existed before the medieval castle. Archaeological evidence suggests that the hill may have been occupied during the Iron Age, potentially more than 2,000 years before the castle was built. Earthworks and defensive features hint at an earlier hill fort, although much of the evidence has been disturbed by later construction. If an Iron Age fortress once occupied the summit, its builders would have faced many of the same engineering challenges encountered by medieval builders. They would have needed to stabilize slopes, organize labor, transport materials, and establish defensible structures on difficult terrain. Yet no detailed record survives to explain how these tasks were accomplished. The possibility that multiple generations of builders reused and modified the same strategic location over centuries adds another layer of complexity to the site's history. Water management presents one of the castle's greatest engineering mysteries. Every successful fortress required a dependable water supply. During a siege, lack of water could prove more dangerous than enemy soldiers. Yet Dinas occupies an isolated summit with no obvious natural spring. Historians and archaeologists continue to debate how the inhabitants secured water. Some propose sophisticated rainwater collection systems. Others suggest hidden storage cisterns or now-lost access routes leading downhill toward water sources. Excavations have produced clues but no definitive solution. The problem becomes even more intriguing when one considers that medieval military planners fully understood the importance of water security. The fact that the castle was built at all suggests that a viable solution existed. The fact that the solution remains unclear today highlights how much practical engineering knowledge has been lost. The defensive design itself raises additional questions. Computer simulations conducted on comparable medieval fortifications show that carefully positioned walls could dramatically increase defensive effectiveness. At Dinas Bran, surviving sections indicate that builders exploited every advantage offered by the terrain. Attackers approaching the summit would have been forced into narrow routes exposed to defenders positioned above. Blind spots appear surprisingly limited. Defensive fields of view overlap efficiently across critical access points. Such optimization suggests a sophisticated understanding of battlefield geometry. Yet no architectural plan survived to explain how these calculations were made. Whether achieved through experience, experimentation, or inherited military traditions, the final result demonstrates a level of practical expertise that remains difficult to quantify. Perhaps the most enduring mystery involves the legends surrounding tunnels beneath the hill. Local folklore speaks of hidden passages extending from the castle into the surrounding landscape. Similar stories appear throughout Britain, often attached to ancient fortifications and castles. Most alleged tunnel networks have never been verified. However, advances in ground-penetrating radar and geophysical surveying have revealed unexpected subterranean structures at numerous archaeological sites around the world. At Dinas Bran, only limited subsurface investigations have been conducted. The possibility that natural cavities, storage chambers, escape routes, or undocumented structures remain concealed beneath the limestone cannot be completely dismissed. Until comprehensive surveys are undertaken, the mystery remains unresolved. Another fascinating question concerns communication. The castle's elevation provided extraordinary visibility across the region. Some researchers have suggested that sites like Dinas Bran may have participated in broader signalling networks using fires, smoke, reflective surfaces, or beacon systems. Across medieval Britain, chains of elevated sites allowed messages to travel rapidly across larger distances. If Dinas Bran formed part of such a network, it would demonstrate a sophisticated understanding of landscape-scale communication. Unfortunately, surviving evidence is insufficient to determine the exact role the fortress may have played. Cubba stood deep within the dry limestone hills of the Puch region in northern Yucatan, Mexico. A Maya city discovered by European explorers in the mid-19th century after centuries of abandonment beneath dense tropical vegetation. Archaeologists were immediately confused by what they found. Massive stone palaces still standing after more than 1,000 years. Thousands of perfectly shaped decorative stones fitted together with astonishing precision. Sophisticated water systems in one of the driest parts of the Maya world, and an architectural style so advanced that some researchers compared parts of it to engineered modular construction. Even today, Cubba remains one of the most technologically mysterious cities ever built by the ancient Maya. The first large scientific surveys began in the 1840s when explorers John Lloyd Stevens and Frederick Catherwood documented the ruins in remarkable detail. Catherwood's drawings revealed entire palace walls covered in repeated stone masks of the rain god Chak. At first, archaeologists believed the structures were mostly ceremonial, but later excavations showed Cubba had been a densely populated urban centre connected to a much larger regional infrastructure system. Modern LIDAR surveys and geological studies now suggest the city was engineered with a level of environmental planning far beyond what was once believed possible for pre-industrial Mesoamerica. One of the greatest mysteries surrounding Cubba is the extraordinary precision of its stonework. The city belongs to the Puch architectural tradition, famous for highly detailed mosaics and geometric facades. But at Cubba, the level of repetition becomes almost industrial. The Cod's Poop, often called the Palace of the Masks, contains over 250 stone masks of chalk attached to its outer walls. Each mask consists of multiple carved blocks fitted together to form curved noses, symmetrical eyes, and layered geometric details. Many stones align so tightly that even modern researchers struggle to insert thin blades between the joints. This becomes more mysterious when considering the tools available to the Maya. They had no iron tools, no steel chisels, and no beasts of burden capable of transporting heavy blocks efficiently. Most carving was supposedly done using stone hammers, harder limestone, and obsidian cutting edges. Yet certain surfaces at Cubba display flatness and angular consistency, approaching machine-like accuracy. Some blocks show repeated dimensions across different buildings, leading a few researchers to speculate that the Puch Maya may have developed standardized stone templates or modular construction techniques centuries ahead of their time. The engineering challenge becomes even greater when examining the environment itself. Unlike many other Maya cities located near cenotes or permanent rivers, Cubba existed in a region with severe seasonal droughts. Northern Yucatan receives roughly 900 to 1,100 millimeters of rainfall annually, but most of it arrives during only part of the year. Surface water is nearly absent due to the porous limestone bedrock. For a large city to survive here, advanced water management was absolutely essential. Archaeologists later uncovered one of Cubba's most fascinating technological systems, underground water reservoirs known as chultuns. These bottle-shaped chambers were carved directly into limestone and coated with waterproof plaster. Rainwater from plazas, rooftops, and paved surfaces was carefully redirected through sloped channels into storage chambers below ground. Some chultuns could hold tens of thousands of liters of water. What astonished engineers was the efficiency of the design. The slope angles had to be calculated carefully enough to move water across uneven limestone terrain without losing too much to seepage or evaporation. Some reservoirs still preserve traces of hydraulic plaster after more than a millennium underground. Researchers have compared the sophistication of these systems to early urban water management technologies seen in parts of the Roman world and ancient Persia. The plaster itself remains another major mystery. Laboratory analysis suggests the Maya heated limestone at extremely high temperatures to produce lime mortar strong enough to survive tropical humidity for centuries. Some sections of Puch masonry show unusual resistance to biological erosion despite constant exposure to roots, fungi, moisture, and acidic rain. Scientists studying ancient mortars have compared certain Maya mixtures to Roman volcanic concrete because both appear unusually durable compared to many later historical materials. Even more puzzling is how Kaba's buildings maintain structural stability despite their construction style. Unlike Egyptian pyramids or Roman concrete domes, Puch buildings often relied on relatively thin outer stone veneers surrounding rubble cores. In theory, many of these structures should have collapsed long ago after internal deterioration, yet several major facades remain standing with surprising integrity. Modern structural analysis suggests Maya builders may have understood sophisticated load distribution principles. Certain arches and corners use gradual stone size variation to redirect pressure away from weak points. Corbel vaults inside Kaba's palaces were designed so weight compressed inward rather than downward directly onto entrances. Similar stress distribution concepts appear in much later medieval stone architecture in Europe. Yet the Maya developed them independently centuries earlier. Another unexplained feature is the Sakbi system connecting Kaba to nearby Maya cities, especially Uxmal. A raised white limestone road stretches roughly 18 kilometers between the two cities. Archaeologists estimate enormous labor would have been required to level terrain, transport stone, and maintain the elevated roadway through dense tropical conditions. The road was not simply functional infrastructure. Its reflective white surface likely glowed under moonlight, suggesting ceremonial or astronomical significance. Some researchers believe the Sakbi functioned as a political symbol demonstrating centralized regional authority. Others argue its alignment may have had ritual or celestial meaning connected to Venus cycles or seasonal movement patterns important in Maya cosmology. Kaba also contains evidence of surprisingly advanced urban planning. Buildings were not randomly positioned. Many align with solar directions or seasonal light events. The arrangement of plazas appears designed to maximize runoff collection during heavy rains while reducing erosion during storms. Certain elevated structures were strategically positioned to improve airflow and reduce heat accumulation in the humid tropical climate. This environmental adaptation becomes especially impressive when compared to many later colonial settlements in the same region that struggled with water shortages and heat management despite possessing metal tools and imported European engineering knowledge. One of the darkest mysteries surrounding Kaba is its sudden decline. The city flourished between roughly 600 and 900 CE during the late Classic Maya period. Then, within a relatively short historical window, major construction stopped and the population collapsed. Unlike some other Maya centers, Kaba does not show widespread evidence of catastrophic warfare or complete structural destruction. Climate studies from lake sediments across the Yucatan indicate severe drought cycles struck the Maya world between the 9th and 10th centuries. Some droughts may have reduced rainfall by as much as 40% for extended periods. But this explanation alone creates another mystery. Kaba was already specifically engineered for water scarcity. If any Maya city should have resisted drought, it may have been Kaba. Some archaeologists believe the collapse was caused not by a single disaster but by systemic failure. Maintaining reservoirs, roads, plaster production, and large ceremonial complexes required enormous labor coordination. Once political authority weakened, the infrastructure itself may have become impossible to sustain. Others suggest regional trade breakdowns or ecological exhaustion, gradually destabilized the city. Do you think the Maya discovered engineering knowledge that modern civilization still doesn't fully understand? Share your thoughts in the comments below. At an altitude of over 5,000 meters in the remote reaches of the Himalayas, a small glacial lake appears unremarkable for most of the year. Frozen, isolated, and inaccessible, it blends into a landscape shaped by ice and silence. But when the snow melts, the surface reveals something that should not exist in such numbers or in such a place. Hundreds of human skeletons scattered along the edges of the water, preserved by cold and time. The problem is not simply that these people died here. The problem is that they did not die together, did not come from the same place, and yet appear to have met the same end. Rupkund Lake is not a single mystery. It is a pattern of events repeating across centuries without a clear explanation. The modern story begins in 1942, when a British forest ranger, patrolling the region during the late colonial period of India, came across a disturbing sight. As the ice receded, human bones began to emerge across the lake bed and surrounding slopes. Initial assumptions were shaped by the context of the time. With the Second World War underway, officials speculated that these might be the remains of Japanese soldiers who had attempted an incursion through the mountains. However, closer inspection quickly dismantled this theory. The skeletal remains showed clear signs of age far beyond a few decades. No modern weapons, uniforms, or equipment were found. Instead, artifacts such as wooden tools, leather footwear, iron spearheads, and rings suggested a much older origin. What began as a wartime curiosity immediately transformed into an archaeological anomaly. By the 1950s and 60s, systematic examinations of the bones began. Anthropologists noted that many of the skeletons were remarkably well preserved due to the freezing conditions, allowing for detailed study. One of the most striking findings was the pattern of injuries. A large proportion of skulls displayed circular fractures, consistent with blunt force trauma delivered from above. These were not random breaks caused by erosion or animal activity. The injuries were concentrated on the top of the skull, with minimal damage to other parts of the body. This distribution ruled out close combat or interpersonal violence. Instead, it suggested a sudden, external force acting vertically. Based on these observations, researchers proposed a hypothesis grounded in environmental physics. At high altitudes, hailstorms can produce ice projectiles with diameters exceeding 5 centimeters and impact velocities sufficient to fracture bone. If a group of individuals were caught in an exposed area without shelter, repeated impacts could cause fatal head injuries within minutes. This explanation aligned with both the injury patterns and the lack of defensive wounds. However, it did not explain who these people were, why they were there, or why so many died in the same location. In the early 2000s, advances in radiocarbon dating provided the first reliable timeline. Initial tests suggested that a significant portion of the remains dated to approximately the 9th century. This placed the event more than 1,000 years before the modern discovery. The implication was clear. These individuals were not linked to any recent historical conflict, but to a much older, undocumented event. The number of individuals estimated between 200 and 800 indicated that this was not a small group. It was a large, organized movement of people. Further analysis of clothing fragments and artifacts revealed diversity within the group. Some individuals wore simple, practical garments consistent with local populations. Others were associated with more elaborate items, including ornaments and decorated objects. This suggested a mixed group, possibly including both common travelers and individuals of higher social status. One hypothesis proposed that they were part of a pilgrimage, possibly connected to ancient Himalayan religious practices. Yet, no written records from the period clearly describe such a large group meeting this fate in this location. In 2019, a comprehensive genetic study introduced a new layer of complexity. Using ancient DNA sequencing, researchers analyzed dozens of individuals from the site. The results fundamentally altered the understanding of Rupkund. Instead of a single group, the remains belonged to at least two distinct populations separated not only by geography, but also by time. One group was consistent with South Asian ancestry and dated to around the 8th to 10th centuries. This aligned with earlier radiocarbon findings and supported the pilgrimage hypothesis. However, a second group displayed genetic markers most closely associated with populations from the Eastern Mediterranean, including regions such as Greece and Crete. Even more surprising was the dating of this group. They appeared to have died roughly 1,000 years after the first group. This created a contradiction that current historical models struggle to resolve. There is no clear evidence of large-scale Mediterranean travel into this specific region of the Himalayas during that period. Nor is there an explanation for why these individuals would have followed a path leading to such an isolated and hazardous location. The presence of two unrelated groups, separated by centuries, yet ending up in the same lake, suggests that Rupkund is not the result of a single historical event. When all evidence is considered together, a pattern begins to emerge. Multiple groups from different regions and different centuries arrived at the same high-altitude lake. Each group appears to have died suddenly, with similar trauma concentrated on the skull. There is no evidence of long-term habitation, no signs of burial practices, and no indication that survivors remained to document the event. The deaths were abrupt and final. From a scientific perspective, the most consistent explanation remains extreme weather, specifically high-energy hailstorms. At elevations above 5,000 meters, atmospheric conditions can produce localized events of extraordinary intensity. Without modern forecasting or protective equipment, ancient travelers would have had no warning and no means of escape. Yet, this explanation raises its own questions. Why did multiple groups choose this route? Why were they exposed at precisely the same vulnerable location? And why does the pattern repeat across such long intervals? Rupkund Lake challenges the assumption that archaeological sites represent isolated events. Instead, it suggests the possibility of recurring environmental hazards interacting with human movement in ways that are not fully documented. The combination of radiocarbon dating, forensic analysis, and genetic data creates a layered narrative that does not resolve into a single conclusion. Each new discovery has added clarity to individual aspects: how they died, when they died, and where they came from, but has also expanded the scope of the mystery. If a single natural mechanism can produce identical outcomes across centuries, then Rupkund may represent a broader class of sites where environmental risk is underestimated or misunderstood. Alternatively, if there are missing historical connections, trade routes, undocumented migrations, or lost cultural practices, then the lake may be a fragment of a much larger story that has not yet been reconstructed. If multiple groups, separated by centuries and coming from entirely different regions, all ended up dying in the exact same way at the same location, do you think Rupkund is just a natural hazard repeated over time, or are we missing a deeper pattern behind these events? Share your thoughts in the comments below. Port Einon, Gower Peninsula, South Wales. Beside a windswept bay facing the Atlantic Ocean stand the remains of a small stone structure known as the Port Einon Salt House. At first glance, it appears insignificant compared to castles, cathedrals, or ancient monuments. Yet hidden within these ruined walls is a technological mystery that continues to puzzle historians today. How did a small coastal operation produce large quantities of salt in a cold climate while consuming far less fuel than modern calculations suggest should have been possible? The surviving structure was identified as a historic salt production facility through archaeological investigations, historical records, and the discovery of industrial features associated with salt boiling. Excavations revealed evidence of furnaces, evaporation areas, and specialized construction designed for long-term operation in an aggressive marine environment. What researchers expected to find was a simple medieval workshop. What they discovered instead was evidence of surprisingly sophisticated engineering. Of all the unanswered questions surrounding Portaenon Salt House, none is more fascinating than the mystery of its production efficiency. Salt may appear simple, but producing it from seawater is an extremely energy-intensive process. Modern seawater contains approximately 35 grams of dissolved salt per litre. This means that producing a single metric ton of salt requires processing roughly 28 to 30 cubic meters of seawater. In practical terms, more than 28,000 litres of water must be evaporated. The problem becomes even more difficult in Wales. Unlike the Mediterranean, South Wales experiences frequent cloud cover, lower average temperatures, and significantly less solar evaporation. These conditions make traditional solar salt production inefficient, yet historical evidence suggests that Portaenon was commercially viable. This creates a technological puzzle. If operators relied entirely on direct boiling, fuel consumption would have been enormous. Experimental archaeology suggests that medieval salt production could require several tons of wood for every ton of finished salt. Such consumption would quickly exhaust local fuel supplies. So how did the Portaenon producers solve this problem? One theory proposes that they developed a multi-stage concentration process before boiling began. Instead of heating fresh seawater immediately, they may have first concentrated brine naturally through wind exposure and shallow holding ponds. By allowing Atlantic winds to remove part of the water content, the final boiling stage would require far less energy. The concept resembles techniques documented in French salt marshes and certain Roman salt works. However, no complete evidence for such a system has been found at Portaenon. Another possibility is even more intriguing. Researchers have suggested that local operators may have understood tidal concentration zones. Certain coastal pools can naturally accumulate higher salinity water due to repeated evaporation and tidal cycles. Harvesting water from these locations would dramatically improve production efficiency. If true, the workers possessed practical environmental knowledge that effectively functioned as a form of applied chemistry centuries before modern chemical science existed. Yet the greatest mystery remains the absence of technical documentation. No surviving manuals explain the process. No engineering plans describe the production system. The physical structure survives, but the knowledge behind it has largely disappeared. Salt is one of the most destructive substances for masonry. Modern engineers constantly battle salt crystallization, moisture penetration, and chemical degradation in coastal structures. Even reinforced concrete often suffers severe damage after decades of exposure to marine environments. Portaenon Salt House faced a far harsher challenge. Its walls endured centuries of sea spray, Atlantic storms, humidity, and concentrated salt vapors generated during production. Yet significant portions of the structure remain standing. This raises questions about the materials used by its builders. Analysis suggests the mortar was likely produced using local limestone and shell-derived lime. However, researchers still debate why certain sections appear unusually resistant to marine deterioration. Some specialists have compared the phenomenon to the remarkable durability of Roman maritime concrete. While the materials are not identical, both cases suggest that historical builders may have understood local mineral properties far better than previously assumed. Were the builders intentionally selecting specific aggregates? Did repeated exposure to seawater alter the chemistry of the mortar in beneficial ways? The exact answer remains uncertain. Producing salt through boiling creates an enormous amount of steam. Without effective ventilation, working conditions become nearly impossible. High humidity reduces combustion efficiency, damages structures, and creates dangerous conditions for workers. Yet the surviving layout suggests that airflow may have been carefully controlled. Openings appear positioned to capture prevailing Atlantic winds. Some researchers believe the building may have functioned as a passive ventilation system using natural pressure differences to remove steam while maintaining efficient combustion. The concept resembles principles employed in modern industrial ventilation systems. If accurate, the builders achieved this without mathematical fluid dynamics models, computer simulations, or modern engineering tools. How they optimized airflow remains unknown. Perhaps the greatest logistical question concerns energy. Boiling tens of thousands of liters of seawater requires massive amounts of fuel. Historical estimates suggest that large-scale salt production operations could consume several tons of fuel each week. Where did Port-Énon obtain enough energy to remain operational? The surrounding landscape could not indefinitely support unrestricted wood harvesting. Some historians believe fuel arrived by boat from other regions. Others suggest that coal may have been incorporated into the process earlier than historical records indicate. South Wales sits near some of Britain's richest coal deposits. If coal was being used systematically, it would significantly improve efficiency. Unfortunately, definitive evidence remains elusive. Salt was a valuable commercial commodity. It preserved food, supported fishing industries, and served numerous industrial purposes. For Port-Énon to operate successfully, transportation infrastructure must have existed. Large quantities of salt could not simply be carried away by hand. Archaeologists suspect that docks, loading platforms, storage facilities, and maritime support structures once surrounded the site. Almost all of these features have vanished. Centuries of coastal erosion and Atlantic storms may have destroyed critical evidence. As a result, researchers are attempting to reconstruct an entire industrial network from only a handful of surviving clues. The location of the salt house itself may represent a sophisticated engineering decision. The structure occupies a position that balances access to seawater, protection from extreme wave action, and proximity to transportation routes. Modern coastal engineering relies heavily on hydrodynamic modeling and environmental analysis to make such decisions. The builders possessed none of these tools, yet their choice proved remarkably successful. The site survived for centuries in one of the most challenging coastal environments in Britain. Was this simply experience accumulated over generations? Or did medieval coastal engineers possess a practical understanding of environmental systems far more advanced than historians once believed? Perhaps the greatest mystery is not the building itself, but the loss of the knowledge that created it. The engineers behind Port-Énon Salt House mastered fuel use, heat transfer, materials, and production organization, turning seawater into a valuable commodity under difficult conditions. Yet little of their expertise survives. No detailed manuals, blueprints, or records explain how they optimized brine, designed furnaces, or improved efficiency. The stones remain, the evidence remains, but the methods are largely gone. What do you think? Were the engineers of Port-Énon simply masters of practical experience, or did they possess production techniques that have been lost to history? Share your thoughts in the comments below. Entire island in the Aegean Sea was reshaped into a geometric pyramid thousands of years before classical Greece ever existed. Rising from the waters near the sacred island of Keros, Daskalio appears, at first glance, to be a natural rocky outcrop. But beneath its slopes lies evidence of something far more unsettling. Not a structure built on an island, but an island that was transformed into a structure. During the early Bronze Age, between approximately 2800 and 2300 BCE, human hands carved, transported, and assembled thousands of tons of stone to impose a deliberate, terraced geometry onto this small landmass. The result is a form so precise that from above it resembles a stepped pyramid, an architectural concept that should not exist in this place at this time with the tools available. What kind of society reshapes an island? And more importantly, why? The story of Daskalio begins not with the island itself, but with a mystery uncovered nearby. In the 20th century, archaeologists working on Keros began finding thousands of fragmented Cycladic marble figurines. These were not ordinary remains. The statues had been deliberately broken, their pieces transported from multiple islands across the Aegean, then deposited in a specific area on Keros. Radiocarbon dating and stylistic analysis placed them firmly within the early Bronze Age, suggesting a coordinated ritual practice spanning generations. This phenomenon became known as the Keros Hoard, one of the earliest large-scale ritual depositions ever discovered in Europe. But one question remained unresolved. Where did the people who performed these rituals live? Attention gradually shifted to Daskalio. Early surveys suggested minimal activity, almost dismissing it as an insignificant rocky extension of the surrounding landscape. But systematic excavations led by institutions such as the University of Cambridge and the British School at Athens would reveal something far more complex. Beneath layers of rubble and erosion, archaeologists uncovered terraces, walls, stairways, and structures arranged in a highly organized pattern. What had once been dismissed as a barren rock was, in fact, a densely built environment, one that had been deliberately engineered. As excavation progressed, each campaign brought new and increasingly unexpected discoveries. The earliest phases revealed that Daskalio had not always been an island. Geological analysis indicates that during the early Bronze Age, lower sea levels connected it to Keros by a narrow land bridge. This meant the site was originally part of a larger ritual landscape rather than an isolated outpost. Subsequent excavations uncovered extensive terracing systems. These were not random accumulations of stone. The retaining walls were carefully constructed using imported marble blocks, many sourced from the island of Naxos, located approximately 10 kilometers away. The scale of this effort is striking. Estimates suggest that thousands of tons of marble were transported across open water and then hauled up the steep slopes of Daskalio. The terraces were arranged in successive levels, creating a stepped profile that reshaped the natural topography into a controlled architectural form. Further discoveries revealed buildings, narrow pathways, drainage systems, and evidence of metallurgical activity. Crucibles, molds, and slag deposits indicate that copper processing took place on site, suggesting that Daskalio was not merely symbolic, it was functionally active. By the time excavations reached deeper layers, a picture began to emerge. Daskalio was a densely occupied, highly organized settlement integrated with the ritual activities on Keros. Among all the mysteries surrounding Daskalio, one stands above the rest in terms of sheer improbability: the transportation of its building materials. The marble used in construction does not originate from the island itself. Geological sourcing confirms that much of it came from Naxos, requiring extraction, shaping, and transport across approximately 10 kilometers of open sea. In the absence of advanced ships, cranes, or mechanical lifting systems, this process becomes difficult to reconstruct with certainty. Experimental archaeology suggests that Bronze Age communities may have used wooden sledges, rollers, and simple rafts. However, scaling these methods to account for thousands of tons of material introduces significant logistical challenges that are still not fully resolved. Even under ideal conditions, transporting a single block weighing several hundred kilograms would require coordinated labor, stable watercraft, and precise timing. Repeating this process hundreds or thousands of times implies a level of organization that approaches that of later, more complex civilizations. The comparison with Stonehenge is unavoidable. At Stonehenge, stones weighing up to 25 tons were moved over distances exceeding 200 kilometers. Yet despite decades of research, the exact methods remain debated. Daskaleo presents a similar paradox on a smaller scale, but within a maritime environment. Instead of overland transport, materials had to cross open water, introducing variables such as currents, weather conditions, and buoyancy constraints that significantly complicate any reconstruction model. Another comparison can be drawn with the Great Pyramid of Giza, where millions of limestone blocks were quarried and assembled with remarkable precision. In Egypt, the presence of a centralized state and a large organized labor force offers a partial explanation for such an undertaking. At Daskaleo, however, no clear evidence of a centralized authority has been identified. Yet the outcome, a transformed landscape requiring sustained effort over time, suggests coordination at a regional scale, possibly involving multiple island communities working toward a shared objective. What makes this problem particularly unresolved is not the possibility that transport occurred, but the absence of direct evidence detailing how it was achieved. No preserved boats, no clear harbour installations, and no definitive transport tools have been found. The result is a gap between capability and evidence, a hallmark of many ancient engineering mysteries. The purpose of Daskaleo remains one of the most debated aspects of the site. One interpretation views it as a ritual centre directly connected to the activities on Keros. The deliberate fragmentation of figurines and their deposition suggests a shared symbolic system across multiple communities, indicating that Daskaleo may have functioned as a ceremonial hub where people gathered to participate in structured rituals. Another interpretation emphasizes its industrial features. The presence of metallurgical remains indicates that copper processing occurred on site, raising the possibility that Daskaleo served as an early production center linked to emerging trade networks in the Aegean. A third perspective considers Daskaleo as a proto-urban environment. The density of structures, the organization of space, and the integration of infrastructure point toward a form of settlement that predates classical urbanism. Each interpretation, however, introduces contradictions. A purely ritual site would not require such extensive infrastructure. A purely industrial site would not explain the symbolic significance of the figurine deposits. And a proto-city located on a steep, resource-limited island challenges conventional models of early urban development. These contradictions are precisely what make Daskaleo so compelling as an archaeological puzzle. It resists simple classification, existing instead at the intersection of multiple functions and meanings. If a society with limited tools could reshape an entire island into a geometric structure, what other achievements might have existed and simply vanished without leaving a clear trace? Dolphin Castle, located near Montgomery in Powys, Wales, was identified through 19th century antiquarian surveys before large-scale archaeological investigations revealed the remains of one of medieval Wales' most ambitious native fortresses. Built around AD 1273 by Llywelyn ap Gruffydd, the last independent Prince of Wales, the castle stands on a prominent ridge overlooking the Severn Valley. At first glance, Dolphin appears to be just another ruined medieval stronghold. However, beneath its weathered stone walls lies a series of engineering mysteries that continue to challenge archaeologists, military historians, and construction experts. More than 7 centuries after its fall, the castle still raises important questions about surveying methods, logistics, defensive architecture, hydrological engineering, and the disappearance of the technical knowledge that once enabled builders to construct powerful fortifications in some of the most challenging landscapes in Britain. The first mystery begins with the selection of the castle's location. Modern topographical analysis shows that Dolforwyn occupies an exceptionally advantageous position. The ridge provides extensive visibility over strategic routes connecting central Wales with the English borderlands. Military studies suggest that observation from elevated defensive positions can extend early warning capabilities by several kilometres, giving defenders valuable time to prepare for approaching forces. What puzzles researchers is how 13th century builders identified such an optimal site without modern surveying equipment. The ridge itself is narrow, uneven, and surrounded by steep slopes. Yet the castle was positioned almost exactly where the natural terrain offered the greatest defensive advantage. Similar questions arise regarding Machu Picchu in Peru and the hilltop fortresses of the Inca Empire. In each case, ancient builders selected locations that modern geographical analysis confirms were remarkably effective. The methods used to identify these sites remain largely undocumented. Archaeological investigations reveal that Dolforwyn's design differed significantly from many contemporary Norman castles. Rather than imposing a symmetrical layout on the landscape, the builders adapted every section of the fortress to the natural contours of the hill. The curtain walls curve, vary in thickness, and follow irregular lines. For centuries, historians assumed this asymmetry reflected limited engineering capability. Recent analyses, however, suggest the opposite. Computer simulations of attack scenarios indicate that irregular wall geometry often created overlapping fields of fire, improving defensive effectiveness. Certain sections of the walls were deliberately reinforced, while others relied more heavily on natural slopes. Modern military engineers refer to this concept as terrain integration, a strategy in which natural geography becomes an integral part of the defensive system. The mystery lies in whether medieval Welsh builders developed these solutions through trial and error, or possessed a more sophisticated understanding of a defensive geometry than surviving records suggest. The transportation of construction materials presents another unresolved question. Estimates suggest that thousands of tons of stone were used to build Dolforwyn Castle. Much of this material had to be quarried, shaped, transported, and lifted to the top of a steep hill. Experimental archaeology projects have demonstrated that moving large stone blocks without mechanized equipment requires enormous manpower and careful coordination. A single block weighing several hundred kilograms may require dozens of workers using ropes, sledges, rollers, and temporary ramps. Yet no surviving documents describe how the builders organized this effort. Similar logistical mysteries appear throughout history. The construction of the pyramids involved moving approximately 6 million tons of stone. The builders of Sacsayhuaman transported blocks weighing more than 100 tons. Although Dolforwyn was smaller in scale, the fundamental question remains the same. How were labour forces coordinated, supply chains maintained, and construction schedules managed without detailed technical documentation? Equally fascinating is the durability of the surviving stone walls. Wales experiences substantial rainfall throughout the year. In many regions, annual precipitation exceeds 1,000 millimetres. Such conditions typically accelerate erosion, weaken mortar, and increase damage caused by freeze-thaw cycles. Nevertheless, much of Dolforwyn's masonry remains standing after more than 700 years. Material analyses indicate that medieval lime mortar was used throughout the structure. Even so, researchers continue to debate whether local craftsmen employed specialized mixtures optimized for the Welsh climate. Comparable studies of Roman concrete have revealed chemical processes that allowed structures to survive for millennia. Research published in recent years has shown that Roman marine concrete can actually become stronger through interaction with seawater. Did medieval Welsh masons possess practical knowledge of mortar formulations that has since been lost? Although there is no evidence of any extraordinary lost material, the precise techniques used to maximize durability remain poorly understood. One of the most intriguing mysteries concerns water management. A fortress can survive a siege only if it maintains a reliable water supply. Historical records show that medieval sieges sometimes lasted for months or even years. The famous siege of Kenilworth in England, for example, lasted approximately 6 months during the 13th century. Dolfawin was built on a ridge without an obvious natural spring capable of supplying a large garrison. Archaeologists have identified cisterns, drainage channels, and collection systems that were likely used to capture and store rainwater. The question is whether the surviving remains represent the entire system. Hydrological studies indicate that even relatively small catchment areas can collect significant amounts of water in regions with high annual rainfall. Some researchers believe that the original water management network may have been far more sophisticated than current evidence suggests. If true, Dolfawin would represent an impressive example of medieval environmental engineering. Another mystery involves structural stability. Castle walls are not merely vertical barriers, they must withstand their own weight, environmental stresses, ground movement, and potential attacks. Modern structural engineering relies on mathematical calculations to estimate loads and stresses. Medieval builders did not possess formal engineering equations in the modern sense, yet their structures often demonstrate remarkable stability. At Dolfawin, the foundations were adapted to uneven bedrock and varying soil conditions. The builders appear to have understood where additional reinforcement was necessary and where natural rock formations could safely bear structural loads. This practical knowledge resembles what has been observed at many other historic sites, including Europe's great cathedrals and the fortifications of the Crusader states. These structures survived because their creators understood structural behavior, even if they expressed that knowledge through experience rather than mathematics. The military effectiveness of Dolfawin presents another puzzle. In 1277, King Edward IV of England captured the castle during his campaign against Welsh independence. Yet modern analysis suggests that the fortress was far from weak. Defensive studies indicate that attackers advancing uphill would have been exposed to missile fire for extended periods. The narrow ridge restricted troop movement and prevented large assault formations from advancing efficiently. Archaeologists have identified features suggesting deliberate planning aimed at maximizing defensive advantages. Had circumstances been slightly different, the fortress might have resisted for much longer. This raises an intriguing possibility. Was Dolfawin merely a regional stronghold, or was it an experimental expression of an evolving Welsh military architecture? The final and perhaps greatest mystery is the loss of the knowledge itself. Dolfawin's builders clearly possessed advanced skills in surveying, construction, and military design developed over generations. Yet little of this expertise survives. No manuals, engineering texts, or records explain how they measured, built, organized labor, or managed construction. Remains of the Dolgarrog Dam disaster, located in the Conwy Valley of North Wales, mark the site of one of Britain's most devastating engineering failures. The disaster occurred on November 2, 1925, when the upper reservoir of the Dolgarrog hydroelectric scheme suddenly collapsed, releasing an estimated 2 billion gallons of water, more than 9 billion litres, into the valley below. The flood raced toward the village of Dolgarrog, destroying homes, bridges, railway infrastructure, and industrial facilities within minutes. Official records documented 16 deaths, although many historians believe the toll could have been far higher had the disaster occurred during the day rather than shortly after midnight. More than a century later, the remains of the failed dam continue to raise questions that engineers, geologists, and historians have never fully answered. The first mystery concerns the exact mechanism that triggered the collapse. Official investigations concluded that exceptionally heavy rainfall filled the reservoir beyond safe levels. However, the explanation was never entirely satisfactory. Rainfall alone rarely destroys a properly designed dam. Modern engineering studies suggest that the rainfall event was merely the final trigger in a chain of hidden failures that may have been developing for years beneath the structure. One of the most intriguing mysteries involves the geology beneath the reservoir. The dam was constructed in a mountainous region dominated by ancient volcanic rocks, fractured bedrock, and natural fault systems. At the time of construction, geological surveys were far less sophisticated than modern investigations. Engineers lacked ground-penetrating radar, satellite imaging, computerized geological models, and advanced subsurface scanning technologies. As a result, much of what existed beneath the foundation remained unknown. Some modern researchers believe that water gradually infiltrated natural fissures hidden within the underlying rock formations. Over time, this seepage may have enlarged existing fractures through a process known as internal erosion. Laboratory studies show that water moving through microscopic cracks can slowly transport sediment particles away from supporting structures. Initially, the process is invisible. Eventually, the erosion creates underground channels large enough to compromise the stability of entire foundations. Similar mechanisms have contributed to dam failures around the world, including several major reservoir disasters during the 20th century. What makes Dolgarrog particularly mysterious is that no one knows how long such erosion may have been occurring. Was it developing for a decade? For a year? Or did it begin shortly after construction was completed? The surviving evidence cannot provide a definitive answer. The second mystery centers on the extraordinary speed of the collapse. Witness accounts describe the failure as sudden and catastrophic. Yet modern structural engineering suggests that large failures are often preceded by warning signs. Tiny movements, increasing seepage rates, unusual water pressure changes, and microscopic cracking typically occur before complete structural collapse. Today, engineers monitor major dams using instruments capable of detecting movements measured in fractions of a millimeter. Satellite-based interferometric radar can identify ground deformation across entire landscapes. Fiber optic sensors can track internal stresses in real time. None of these technologies existed in 1925. The question remains, did Dolgarrog provide warnings that nobody recognized? Some engineers argue that subtle indicators likely existed but went unnoticed because the technology required to detect them had not yet been invented. Others believe the final failure may have occurred so rapidly that even modern monitoring systems would have provided little opportunity for intervention. A third mystery involves the reservoir's drainage and overflow capacity. Every dam must safely manage extreme inflows during periods of intense rainfall. Engineers design spillways to release excess water before dangerous pressures accumulate. Yet historical records suggest that the rainfall preceding the disaster was among the heaviest experienced in the region for many years. Meteorological reconstructions indicate that parts of North Wales received exceptionally high precipitation during the days before the collapse. However, debate continues regarding whether the spillway system was fundamentally inadequate or whether an entirely different failure mechanism bypassed the intended safety systems. Modern hydraulic modelling produces conflicting results. Some simulations suggest that overtopping alone could have initiated structural damage. Other models indicate that overtopping should not have been sufficient to destroy the dam unless hidden weaknesses already existed within the foundation. The discrepancy highlights a frustrating reality. Even with 21st century computational tools, researchers cannot fully reconstruct every condition present on the night of the disaster. Another unresolved question concerns the engineering assumptions used during construction. The Dolgarrog hydroelectric project represented advanced technology for its era. Hydroelectric power was transforming industries across Europe. and engineers were increasingly confident in their ability to reshape landscapes through reservoirs, tunnels, pipelines, and generating stations. Yet engineering history repeatedly demonstrates that confidence can exceed knowledge. Similar lessons emerged decades later during the failures of the Malpasset Dam in France in 1959 and the Vajont Dam disaster in Italy in 1963. In both cases, structures built using sophisticated engineering principles encountered geological conditions that designers had not fully understood. The comparison is striking. At Malpasset, hidden weaknesses within the bedrock contributed to catastrophic failure. At Vajont, an enormous landslide generated a massive wave that overwhelmed the reservoir system, despite the dam itself remaining largely intact. These events demonstrated that geology can be as important as engineering design. Dolgarrog may represent an earlier example of the same principle. The fourth mystery involves the flood itself. Investigators estimated that billions of gallons of water surged into the valley within a very short period. The resulting flood wave moved with extraordinary force. Entire buildings were swept away. Heavy industrial equipment was displaced. Railway infrastructure suffered severe destruction. Hydraulic calculations indicate that floodwaters traveling through narrow valleys can accelerate dramatically due to topographic constriction. As water is forced through limited space, velocity increases while destructive energy rises exponentially. Modern studies of dam break floods show that flow velocities can exceed several meters per second, generating forces capable of moving vehicles, trees, and large structural components. Yet even today, estimates of the exact flood characteristics at Dolgarrog vary considerably. Different models produce different peak flow rates and flood heights. This uncertainty means that some aspects of the disaster remain scientifically unresolved more than 100 years later. Perhaps the most fascinating mystery lies in the physical remains themselves. Fragments of the failed structure continue to provide evidence for modern investigation. Laser scanning, photogrammetry, geological mapping, and digital reconstruction have allowed researchers to study details that previous generations could not examine. Paradoxically, every new analysis seems to create additional questions. Some models suggest the structure should have survived. Others indicate that relatively small defect could have triggered progressive collapse. The competing conclusions reveal how difficult it is to reconstruct historical engineering failures when critical data has been lost. And that leads to the greatest mystery of all, the disappearance of knowledge. Many original construction records no longer survive. Detailed geological observations were never recorded or have been lost. Instrumentation data did not exist. Engineers left behind physical structures, but only fragments of the information needed to fully understand them. The southern coast of Aliki ancient marble quarry was carved apart directly above the Aegean Sea. Massive white marble blocks weighing more than 20 tons were extracted from cliffs so close to the water that some of the quarry now lies underwater. Even today, archaeologists still cannot fully explain how ancient workers cut, polished, and transported stone with a level of precision that seems dangerously unrealistic for the tools officially available at the time. The site was first systematically documented during 19th century archaeological surveys of Thasos, though local fishermen had known about the submerged quarry remains for centuries. Divers later discovered unfinished marble blocks beneath shallow seawater, tool marks preserved in submerged stone, and quarry channels carved directly into the coastal rock. These discoveries revealed that Aliki was not a small regional quarry. It was an industrial-scale marble extraction complex that supplied some of the most important construction projects in the ancient Mediterranean during the Greek and Roman periods. What makes Aliki extraordinary is not simply the amount of marble removed. It is the sophistication of the engineering hidden inside the quarry itself. The entire operation appears optimized with an efficiency that resembles a pre-industrial production system rather than a primitive extraction site. The marble of Thasos was among the purest in the ancient world. Modern mineralogical analysis shows that Thasian marble contains exceptionally high calcite purity, often exceeding 98% calcium carbonate. This gave the stone its famous luminous white appearance and unusually strong light reflectivity. Roman elites considered it one of the finest decorative stones in the empire, comparable to the famous Carrara marble later used during the Renaissance. But purity also created a major technical problem. Highly crystalline marble fractures unpredictably under stress. Extracting large intact blocks without modern machinery should have been extraordinarily difficult. Yet the quarry walls at Aliki contain long extraction channels cut with astonishing consistency. Some grooves run for several meters in nearly straight lines, with remarkably uniform depth. Even modern stonemasons studying the site have noted how difficult it would be to reproduce such precision using only handheld iron tools. Unlike rough quarry marks commonly seen in ancient extraction sites, many cuts at Aliki appear methodical and geometrically controlled. The standard explanation claims workers used iron chisels and wooden wedges. According to this theory, narrow slots were carved into the marble, dry wooden wedges were inserted, and water was added until the expanding wood generated enough pressure to split the stone apart. The method is historically documented in several ancient cultures, but experiments performed on dense marble blocks have shown that the process is highly unstable. Pressure often spreads unevenly through crystalline stone, producing uncontrolled fractures. At Aliki, however, many extracted blocks remained remarkably intact despite their enormous size. Some unfinished blocks still visible at the quarry may have weighed between 15 and 25 tons. Separating stone masses of that scale without catastrophic cracking would require precise understanding of natural stress lines, crystal orientation, and internal weaknesses within the marble. Ancient quarry workers may have possessed practical geological knowledge far beyond what historians traditionally assume. Even more mysterious is the location of the quarry itself. Most ancient extraction centres were established inland where workers could operate safely and move stone gradually toward transport routes. Aliki was carved directly beside steep coastal cliffs exposed to sea wind and wave erosion. Some extraction surfaces descend almost into the water itself. This suggests the quarry was intentionally designed around maritime transport from the beginning. But that creates another unsolved engineering problem. How are multi-ton marble blocks lowered onto ships without modern cranes? No large harbour infrastructure survives at the site. No permanent lifting towers have been found. And the terrain is so uneven that conventional dragging methods would have been extremely dangerous. Some archaeologists believe ancient engineers built temporary wooden ramps coated with lubricants such as animal fat or wet clay to slide blocks downward. Others propose the use of compound pulley systems, similar to those described centuries later by Roman engineers like Vitruvius. Yet none of these theories fully explains the scale of extraction visible at Aliki. The logistical challenge becomes even more astonishing when compared with other ancient quarrying sites. At the Roman granite quarries of Aswan in Egypt, unfinished obelisks demonstrate how difficult hard stone extraction could become, even with enormous labour forces. In contrast, Aliki's marble appears to have been removed with far cleaner separation surfaces and less evidence of catastrophic failures. Unlike granite, marble is softer, but its crystalline structure makes large-scale precision extraction extremely unpredictable. The consistency achieved at Aliki suggests highly refined quarrying techniques developed over generations. But perhaps the greatest mystery of all involves the finishing of the marble itself. Ancient writers described Thasian marble as glowing under sunlight, Modern optical analysis partially confirms those accounts. Because of its calcite composition and low impurity content, polished Thasian marble reflects light deep beneath its surface before scattering it outward again. This creates a soft luminous effect similar to subsurface scattering seen in human skin. It is one reason ancient Greek and Roman sculptures made from high-quality marble appeared almost lifelike under natural light. The problem is that many surviving Thasian marble surfaces exhibit levels of smoothness extremely difficult to achieve with ancient polishing methods. Under microscopic examination, some polished sections reveal abrasion patterns consistent with ultrafine finishing compounds. The surface roughness in certain samples approaches levels associated with advanced polishing abrasives. Officially, ancient craftsmen used sand, emery powder, crushed quartz, and leather polishing techniques. Emery from the island of Naxos was especially prized because of its hardness. However, reproducing the mirror-like finish observed on some Thasian marble, artifacts would have required enormous labour and exceptional consistency. This raises a disturbing possibility. Ancient craftsmen may have understood mineral abrasives and surface finishing chemistry far better than surviving texts suggest. Some researchers speculate that fine polishing pastes containing silica-rich compounds or microscopic abrasive particles may have been used systematically. Others suggest prolonged wet polishing with progressively finer abrasives could gradually reduce surface imperfections to near microscopic levels. What makes the mystery even deeper is durability. Many Thasian marble surfaces retain their brightness despite centuries of exposure to humid sea air and salt erosion. Normally, salt crystallization gradually destroys polished stone surfaces over time. Yet some marble from Aliki still preserves remarkable reflectivity after nearly 2,000 years. This suggests the finishing process may have altered the stone surface in ways not fully understood today. The quarry also contains abandoned blocks frozen mid-extraction, as if work suddenly stopped. Some remain partially attached to the bedrock with extraction grooves already completed around them. Historians debate why the site was eventually abandoned. Economic collapse during the late Roman period may have reduced demand. Earthquakes could have destabilized coastal operations. Pirate raids were common in the Aegean during periods of imperial decline. Rising sea levels may also have submerged parts of the transport system itself. That final possibility is particularly important. If ancient loading platforms, ramps, or harbour structures now lie underwater, then the most critical evidence explaining how Aliki functioned may still be hidden beneath the Aegean Sea. Divers have already identified submerged quarry surfaces extending below modern sea level, suggesting that portions of the industrial complex disappeared gradually beneath the water over centuries. Do you think the lost technology of Aliki was simply forgotten over time? Or was it far more advanced than historians are willing to admit? Share your thoughts in the comments below. Watek Phnom rises from the flat floodplains of northwestern Cambodia, like the remains of a civilization that understood engineering far beyond what historians once believed possible. Archaeologists first documented the temple during French colonial surveys in the late 19th century, but its true complexity only became clear after structural and geological studies revealed something strange. This massive stone monument had survived nearly 1,000 years on unstable tropical soil that should have caused catastrophic collapse centuries ago. Built during the 11th century under the Khmer Empire, Watek Phnom is often overshadowed by Angkor Wat, yet many researchers now believe it may preserve clues about forgotten construction techniques, material science, and environmental engineering that remain only partially understood today. The first mystery begins beneath the temple itself. Battambang sits in a region heavily affected by seasonal flooding, groundwater movement, and soft alluvial sediments. Modern engineers know that constructing multi-thousand-ton stone structures on such terrain is extremely dangerous without deep foundations or reinforced stabilization systems. Yet Wat Ek Phnom has remained standing for almost a millennium despite earthquakes, monsoon cycles, root intrusion and soil movement. Excavations reveal that Khmer builders created layered laterite platforms beneath the temple, possibly designed to distribute weight across unstable ground. Laterite, an iron-rich tropical soil that hardens when exposed to air, acted almost like a primitive concrete. What shocked researchers was the density and compression of these layers. In some areas, the laterite foundation reached compressive strengths, approaching low-grade modern masonry materials after centuries of natural mineralization. The engineering becomes even more puzzling when compared to other ancient civilizations. Roman builders relied on pozzolanic volcanic concrete capable of resisting seawater for over 2,000 years. The Egyptians built pyramids on stable limestone plateaus to minimize subsidence. But Khmer architects faced one of the worst possible environments for long-term stone construction. Tropical wetlands with intense rainfall exceeding 1,300 millimeters annually. Despite this, the temple's central sanctuary remains relatively aligned. Some structural surveys suggest deviations smaller than a few centimeters across sections several meters wide. An astonishing level of stability for medieval Southeast Asian construction. The stones themselves present another unresolved mystery. Many of the sandstone blocks appear tightly fitted with minimal mortar. Some joints are so narrow that even thin blades struggle to pass between them. Historians traditionally argue that Khmer workers used iron chisels, wooden levers, and manual polishing techniques. But microscopic analysis of certain tool marks suggests repetitive abrasion patterns, more consistent with advanced sanding processes than crude hammering alone. Researchers believe quartz sand mixed with water may have been used as an abrasive cutting compound, similar to techniques proposed for ancient Egyptian granite work. However, recreating the same precision using replicated medieval Khmer tools has proven extremely difficult. Even more mysterious is the transportation problem. Some sandstone blocks used at Wat Ek Phnom weigh several tons and likely originated from quarries located dozens of kilometers away. Moving such stones through floodplains and jungle terrain without wheeled heavy machinery would have required enormous coordination. Scholars estimate that transporting a single large block could have demanded hundreds of laborers using wooden sledges, bamboo rollers, and seasonal waterways. Yet, no surviving Khmer texts explain the logistical systems behind these operations. This absence of documentation has fueled speculation that the Khmer Empire possessed organizational and engineering capabilities far more advanced than traditionally assumed. The carvings at Wat Ek Phnom deepen the mystery further. Many pediments and lintels display highly symmetrical geometric patterns and mythological scenes carved with remarkable consistency. Some decorative grooves are only millimeters deep, yet maintain clean proportions after nearly 1,000 years of erosion. Sandstone is softer than granite, but it fractures easily under uncontrolled pressure. Achieving such detail repeatedly would have required extraordinary control over carving angles and force distribution. Certain historians believe Khmer artisans may have employed proportional measurement systems or reusable geometric templates. If true, this would suggest standardized architectural mathematics operating across multiple Khmer temple sites centuries before modern surveying instruments existed in the region. The climate resistance of the structure is equally difficult to explain. Cambodia's environment is among the harshest in Southeast Asia for preserving exposed stone architecture. High humidity accelerates biological growth. while thermal expansion and acidic rainfall gradually fracture mineral surfaces. Yet many laterite sections at Vatek Phnom remain surprisingly durable. Scientific studies on laterite used in Khmer construction found that oxidation of iron compounds over time may create hardened outer shells that naturally protect interior material from rapid decay. In other words, parts of the temple may have slowly strengthened themselves through long-term chemical transformation. This phenomenon has drawn comparisons to Roman marine concrete, which becomes stronger through interaction with seawater crystals over centuries. In both cases, ancient builders may have unintentionally exploited chemical processes modern science only recently began fully understanding. The difference is that Roman engineering texts survived. Khmer engineering methods largely disappeared with the decline of the empire, leaving modern researchers to reconstruct fragmented clues from ruins alone. Another unresolved question involves astronomical alignment. Like many Khmer temples, Vatek Phnom appears carefully oriented along cardinal directions. Certain corridors and gateways align closely with solar movement during specific times of the year. Achieving this level of orientation without magnetic compasses or optical instruments would have required repeated long-term sky observations. Researchers studying Khmer architecture found that many temples across Cambodia share remarkably consistent directional patterns over distances spanning hundreds of kilometers. This suggests the existence of a standardized cosmological or astronomical surveying system. Some scholars propose that Khmer architects tracked solar shadows using fixed observation poles and seasonal horizon markers. Others argue that water reflection techniques may have helped establish visual alignment baselines, but no surviving evidence fully explains how large-scale directional accuracy was maintained across generations. The mystery becomes even greater when considering the immense labor coordination required to keep temples aligned despite uneven terrain and shifting foundations. Hydraulic engineering may hold another hidden clue. The Khmer Empire is famous for massive reservoirs and canal systems surrounding Angkor, but smaller regional temples like Vatek Phnom were also integrated into sophisticated water management networks. Satellite imaging and ground surveys have identified ancient moats, embankments, and channels surrounding the temple complex. These systems likely served religious symbolism, irrigation control, and flood management simultaneously. Some archaeologists believe Khmer hydraulic infrastructure was so advanced that it allowed dense urban populations to survive seasonal climate extremes for centuries. Yet this same system may have contributed to collapse. Paleoclimate studies indicate Southeast Asia experienced severe megadroughts between the 14th and 15th centuries. Tree ring data and sediment analysis suggest alternating cycles of devastating droughts and extreme monsoon flooding destabilized Khmer water networks. If true, Vatek Phnom may represent not just an engineering achievement, but evidence of how even highly advanced civilizations can become vulnerable when environmental systems exceed their ability to adapt. The temple's decline remains strangely silent. Unlike many ancient cities destroyed by invasion or fire, Vatek Phnom appears to have faded gradually. Jungle growth overtook structures, maintenance ceased, religious centers shifted elsewhere. No massive battlefield debris or widespread burn layers clearly explain abandonment. It was as if the civilization sustaining the monument slowly lost the capacity to preserve it. Do you think the Khmer Empire lost ancient engineering knowledge that modern science still cannot fully explain? Share your thoughts in the comments below. Nestled in the remote Vale of Ues in the Black Mountains of southeastern Wales, the ruins of Llanthony Priory preserve one of medieval Europe's most overlooked engineering mysteries. Nearly 9 centuries after its construction, researchers still cannot fully explain how builders transported enormous quantities of stone into such an isolated valley, created structures capable of surviving extreme Welsh weather, and produced mortar whose long-term durability remains difficult to replicate today. The priory was founded around 1100 CE, near an earlier religious site associated with St. David. Archaeological investigations, architectural surveys, material analysis, and modern laser scanning over the last century have revealed a surprisingly sophisticated construction project hidden beneath the ruins. At first glance, Llanthony Priory appears to be another medieval monastic ruin, yet its location immediately raises questions. The priory sits deep within a narrow valley surrounded by steep mountains. Even modern visitors reach the site through winding roads that cut through difficult terrain. During the 12th century, there were no modern roads, no mechanized transportation, and no industrial lifting equipment. Yet builders somehow transported thousands of tons of sandstone and other construction materials into the valley. The nave alone once stretched approximately 60 meters in length, making it comparable in scale to major ecclesiastical structures elsewhere in Britain. The challenge becomes even more impressive when compared with other remote medieval sites. Tintern Abbey, for example, benefited from transportation along the River Wye. Many large Norman cathedrals were constructed near population centres or navigable waterways. Llanthony lacked both advantages. This raises an unresolved logistical question. How were massive quantities of building stone, timber, lime, tools, and food transported into such an isolated location year after year for decades? Historians can estimate the workforce required, but the precise logistical system remains largely undocumented. Before construction could begin, builders faced another challenge: understanding the landscape itself. Modern engineering projects rely on satellite mapping, laser surveying, geological analysis, and digital terrain models. 12th century builders possessed none of these technologies, yet the priory's layout demonstrates remarkable adaptation to local topography. The foundations were positioned to take advantage of stable ground, while minimizing the effects of seasonal runoff descending from the surrounding mountains. Recent surveys indicate that major structural alignments were carefully planned rather than improvised. Drainage paths, wall positions, and foundation levels suggest a sophisticated understanding of terrain behavior. The mystery is not that medieval builders were skilled. The mystery is how they achieved such precision without leaving behind detailed technical records explaining their methods. Across Europe, similar questions surround sites such as Machu Picchu, Mont Saint-Michel, and certain Cistercian abbeys. The structures survive, but the engineering knowledge often does not. Of all the technological puzzles at Llanthony Priory, perhaps none is more intriguing than the mortar itself. The Welsh climate is notoriously harsh on masonry. The region experiences high annual rainfall, persistent humidity, repeated freeze-thaw cycles, biological growth, and centuries of exposure to wind-driven moisture. Under such conditions, many modern cement repairs deteriorate surprisingly quickly. Yet portions of Llanthony's original masonry have survived for nearly 900 years. Scientific analysis has revealed that the mortar is not simply a crude mixture of lime and sand. Microscopic examination has identified complex mineral compositions, variable aggregate sizes, and evidence that builders deliberately adjusted mixtures according to construction needs. Researchers have discovered that many medieval mortars behaved differently from modern Portland cement. Rather than creating an extremely rigid structure, traditional lime mortars remained slightly flexible. This flexibility allowed walls to absorb minor movements caused by temperature changes, moisture fluctuations, and settlement without catastrophic cracking. Some studies of medieval mortars throughout Britain have also identified traces of organic additives, including animal-derived materials, plant products, and other substances that may have influenced curing behavior. The challenge is that no surviving document describes the exact recipe used at Lanthony. Questions remain regarding what type of limestone was selected, how long the lime was burned, what temperatures were achieved in medieval kilns, whether organic additives were intentionally introduced, and how mixtures were adjusted for different structural applications. Modern conservation specialists continue to study surviving mortar samples because understanding these ancient formulas could improve long-term restoration techniques. The mystery becomes even more fascinating when compared with Roman concrete. Roman harbour structures have survived for over 2,000 years, partly because of unique mineral reactions within their cement. Similarly, Lanthony's mortar may contain combinations of materials and construction practices that are not yet fully understood. In other words, the builders may have possessed practical materials science knowledge that was never formally recorded. Water was both a necessity and a threat. The valley surrounding Lanthony receives substantial rainfall. Seasonal streams, groundwater movement, and runoff from mountain slopes constantly interact with the site. Without proper drainage, foundations would gradually weaken, walls would shift, and structural deterioration would accelerate. Archaeological investigations have revealed evidence of sophisticated drainage systems integrated into the priory complex. Channels, culverts, and carefully managed water pathways appear to have directed moisture away from critical structures. What remains uncertain is the full scale of this network. Researchers continue to ask whether builders understood local groundwater patterns, whether drainage routes were planned before construction began, and how engineers predicted water behavior without modern hydrological modeling. Even today, drainage design remains one of the most critical aspects of construction in mountainous regions. The survival of substantial portions of Lanthony suggests that medieval builders solved problems that modern engineers still treat with great caution. The ruins visible today represent only a fraction of the original complex. Many roofs, vaults, upper walls, towers, and timber structures have disappeared, yet surviving architectural evidence indicates that these elements were once highly sophisticated. Stone vaulting in particular required extraordinary precision. Every block had to transfer loads through carefully calculated paths, and small errors could trigger progressive collapse. Builders possessed no structural analysis software, no computer simulations, and no modern understanding of material stress distribution. Yet medieval vaults throughout Europe routinely spanned impressive distances while supporting enormous weights. At Lanthony, surviving remains suggest that similar engineering principles were employed. The question remains, how much of this knowledge was based on mathematical understanding, and how much was accumulated through generations of experimentation? Another overlooked mystery involves sound. Religious architecture was designed not only to be seen, but also to be heard. The original church likely amplified chanting and liturgical music through carefully proportioned spaces. Large stone surfaces reflected sound, while vault geometry influenced resonance patterns. Modern acoustic engineers can model such effects using sophisticated software. Medieval builders could not. Yet many monastic and cathedral spaces across Europe demonstrate acoustic properties that appear remarkably effective. Was this simply trial and error accumulated over centuries? Or did builders possess empirical design principles that have never been fully documented? The answer remains uncertain. What do you think? Were the builders of Lanthony Priory simply masters of experience and observation? Or did they possess engineering knowledge that has largely been lost to history? Share your thoughts in the comments below. The ancient region of Angkor in present-day Cambodia holds one of the strangest engineering mysteries of the Khmer Empire. Baksay Chamkrong rises from unstable tropical ground like a stone anomaly. More than 1,000 years ago, Khmer builders constructed a steep brick pyramid in one of the wettest regions of Southeast Asia, and somehow made it survive heat, monsoon rain, invasive jungle roots, and centuries of erosion. The greatest mystery is not its size. It is the technology hidden inside it. Baksay Chamkrong was built during the 10th century under King Harshavarman I and later completed by Rajendra Varman II. The temple remained largely overshadowed by larger monuments such as Angkor Wat and Bayonne, even though it sits near the royal core of Angkor. Early French archaeologists from the École Française d'Extrême-Orient documented and restored parts of the structure during the early 20th century after thick jungle growth had partially consumed the monument. What researchers found beneath the vegetation was not simply another Khmer temple, but a compact engineering structure filled with unusual construction techniques. The most famous unexplained feature of Baksay Chamkrong is its brickwork. Thousands of red bricks were fitted together with a level of precision that still confuses engineers today. In many sections, the joints between bricks are so thin they are almost invisible to the naked eye. Even thin metal blades struggle to slide between some blocks. This becomes difficult to explain when compared with ordinary medieval brick production. Ancient bricks were usually inconsistent in shape because kiln temperatures fluctuated heavily. Even Roman bricks, among the finest of the ancient world, often show visible mortar layers several millimeters thick. At Baksay Chamkrong, however, some joints appear almost seamless. The biggest question is the binding material. Modern cement did not exist. Traditional lime mortar alone cannot fully explain the near-fused appearance of the walls. Chemical analysis conducted on Khmer brick monuments has detected traces of calcium compounds, silica, organic residues, and plant-based substances inside the joints. Some researchers suspect the Khmer may have used natural resins or organic adhesives derived from tropical plants, later hardened by heat and humidity over centuries. Others argue the builders may have polished or ground the brick surfaces after placement to create tighter fits. Yet no confirmed reconstruction has successfully replicated the exact appearance and durability of the original joints. The precision becomes even more mysterious considering the environment. Cambodia experiences intense thermal stress. Surface temperatures on exposed stone and brick can exceed 50 degrees Celsius under direct sunlight, followed by rapid cooling during monsoon storms. This repeated expansion and contraction normally fractures masonry over time. Modern concrete structures in tropical climates often require maintenance within decades. Baksay Chamkrong has endured for more than 1,000 years. Some material scientists believe the clay source itself may hold the answer. Certain Khmer bricks contain unusually high concentrations of iron and silica, which may have produced stronger vitrification during firing. If kiln temperatures exceeded approximately 900 to 1,000 degrees Celsius, parts of the clay structure could partially glassify, dramatically increasing durability. The problem is that achieving and maintaining such temperatures consistently in the 10th century would have required far more advanced kiln control than historians previously assumed for the Khmer Empire. The result is a paradox. A civilization without industrial machinery produced brick joints and weather resistance that remain difficult to duplicate precisely today. Another major mystery lies beneath the temple itself. Angkor sits on soft alluvial soil saturated with groundwater for much of the year. Modern engineers still face severe foundation problems in similar terrain throughout Southeast Asia. Yet Baksay Chamkrong's core structure has remained standing for over a millennium despite its steep pyramid design. The secret appears to involve laterite, the iron-rich stone used inside much of the temple's core. Laterite behaves unusually compared with ordinary rock. When freshly cut from the ground, it is relatively soft. Once exposed to air, oxidation causes the material to harden significantly over time. Khmer engineers may have intentionally exploited this property. But the real puzzle is drainage. Water pressure destroys many ancient pyramids from the inside as trapped moisture expands and weakens internal layers. Researchers examining Khmer construction techniques believe microscopic voids between laterite blocks may have acted as passive drainage channels, allowing water to escape naturally rather than accumulate. In effect, the temple may have functioned like a breathable structure centuries before modern moisture control engineering existed. Some conservation specialists compare this principle to porous architectural systems used in certain modern flood-resistant buildings. The difference is that Baksay Chamkrong achieved this with pre-industrial materials and without modern geology. The geometry of the temple raises additional questions. Baksay Chamkrong is aligned almost precisely along the east-west axis, despite being constructed without modern surveying equipment. For a 10th century structure in tropical jungle terrain, the directional accuracy is remarkable. This has led some historians to suggest Khmer architects possessed more sophisticated astronomical observation methods than previously believed. Like many Hindu temples, the pyramid symbolized Mount Meru, the sacred cosmic mountain in Hindu cosmology, but symbolic meaning alone does not explain the structural mathematics involved. The staircase angles are extremely steep, approaching levels that increase both construction difficulty and collapse risk. Yet the load distribution has remained stable for centuries. Engineers studying stepped pyramids often note that tiered geometry naturally redirects gravitational force downward and outward, reducing concentrated stress. The Khmer may have understood these principles intuitively through experimentation, long before formal structural mechanics existed. Comparisons are often made with Mesoamerican pyramids such as those of the Maya. However, Maya pyramids were usually constructed in drier climates using limestone cores and thick stucco coverings. Baksay Chamkrong face tropical humidity levels that frequently exceed 80%. Surviving under those conditions is significantly more difficult. The logistics behind the temple remain another unresolved problem. Some laterite and sandstone blocks weigh hundreds of kilograms. The Khmer Empire had no engines, cranes, or industrial transportation systems. Dense jungle and seasonal flooding made overland transport extremely difficult. Researchers believe Angkor's massive hydraulic network may have provided the solution. The Khmer constructed one of the largest pre-industrial water management systems in human history, including reservoirs, canals, and artificial waterways stretching for hundreds of kilometers. Satellite imaging and LiDAR scans have revealed enormous hidden infrastructure beneath the forests surrounding Angkor. Some archaeologists suspect building materials for temples like Baksay Chamkrong were transported partially by water through these canal systems. If true, this would mean the Khmer Empire operated a level of logistical coordination rivaling some early industrial societies. Yet the exact methods remain unknown. No surviving Khmer texts fully describe the engineering process. Perhaps the greatest mystery is simply survival itself. Many Khmer monuments suffered catastrophic deterioration from vegetation, earthquakes, looting, and climate exposure. Tree roots regularly split stone blocks apart across Angkor. Heavy monsoon cycles weaken foundations year after year. Despite this, the core of Baksay Chamkrong still stands. Structural engineers believe the pyramid's layered design may distribute weight more efficiently than flat platform temples of the same era. The steep geometry channels force downward through progressively smaller terraces, reducing internal stress concentrations. Combined with laterite drainage and unusually durable brickwork, the structure effectively became a self-stabilizing system. That possibility changes how historians view Khmer engineering. Instead of relying purely on a massive labor, the builders may have possessed sophisticated empirical knowledge about materials, water behavior, heat resistance, and long-term structural balance. Do you think the builders of Baksay Chamkrong possessed engineering knowledge far beyond what historians believe today? Or are these mysteries simply the result of lost construction techniques? Share your thoughts in the comments below. Gold became a symbol of power, and writing marked the beginning of recorded history. But beneath the plains of northeastern Bulgaria lies evidence of something even more fundamental: a settlement built around salt, not as seasoning, but as currency, as survival, as control. Hidden beneath the landscape, Solnitsata reveals a truth that challenges everything we think we know about early human civilization: that industrial-scale production, economic specialization, and resource-based power structures may have emerged thousands of years earlier than history is willing to admit. This was not a village. This was a system. And systems, once understood, are never simple. The site of Solnitsata, near the modern town of Provadia, first drew archaeological attention in the early 2000s. Excavations led by Bulgarian archaeologists, including teams from the National Institute of Archaeology, uncovered what initially appeared to be a fortified prehistoric settlement. But as layers were peeled back, the narrative shifted dramatically. Radiocarbon dating placed the earliest occupation of the site around 4700 BCE, pushing it firmly into the Chalcolithic period, well before the rise of Mesopotamian city-states. Yet what lay beneath the soil did not resemble a typical early farming community. Instead, researchers found massive quantities of ceramic vessels, thick-walled furnaces, and mineral residues consistent with brine processing. This was not a place where salt was used. This was a place where salt was made. As excavation seasons progressed, the scale of the operation became clearer. Early digs revealed circular pits lined with clay, interpreted as evaporation basins, followed by the discovery of large ceramic containers capable of holding several liters of brine, often showing signs of repeated heating, thermal stress fractures, mineral crusting, and internal salt deposits. By the mid-2010s, archaeologists had identified entire zones dedicated to salt production, including what appear to be proto-industrial kilns. And these installations were not random but organized spatially and functionally, suggesting a workflow of extraction, heating, evaporation, and collection. In later excavation layers, something even more surprising emerged: stone fortification walls, in some places over 2 meters thick, encircling the settlement, indicating this was not a temporary camp, but a deliberately defended site. And with each discovery, a contradiction deepened. How could a community this early, this small, sustain something this complex? At first glance, the technology of Solnitsata seems almost primitive, relying on clay vessels, fire and water, heat it long enough and salt remains. A process so basic that it appears intuitive, but when examined closely, the system begins to unravel into something far more sophisticated. Because to produce salt efficiently through boiling, several variables must be controlled with surprising precision, including temperature stability, where too low slows evaporation, and too high risks, cracking vessels or uneven boiling, volume calibration, where the ratio of brine to container size determines yield and consistency, time cycles, requiring repeated heating sequences that must be maintained to ensure continuous output, and material resilience, as ceramics must endure repeated thermal stress without failure. What archaeologists found at Solnitsata suggests these variables were not merely understood but optimized, as many ceramic vessels display uniform dimensions implying standardization. Residue analysis reveals consistent salinity levels, suggesting controlled input sources, and some kilns appear to have been used continuously over extended periods, indicating sustained and organized production cycles. This is where the paradox emerges, because there is no evidence of formal mathematics, no written instructions, and no measuring tools as we would recognize them, and yet the output behaves as if governed by repeatable, calibrated processes. To understand this anomaly, it helps to compare Solnitsata with sites like Dolny Viestonice, dating back to around 29,000 BCE, where archaeologists discovered ceramic kilns capable of firing clay at temperatures exceeding 600 to 800 degrees Celsius long before metallurgy, demonstrating early mastery of thermal control. But Solnitsata goes further by not only controlling heat, but integrating it into a structured production system. Even in later civilizations, such as ancient China during the first millennium BCE, large-scale salt production required state-level organization, written records, and specialized labor. Yet at Solnitsata, all of this appears to exist without visible state infrastructure, raising a deeper question, not whether the technology was simple, but how something so simple was used with such systematic precision long before systems were supposed to exist. The implications of this production extend far beyond technology, as salt in prehistoric Europe was not merely valuable, but essential for preserving meat, sustaining diets, and enabling long-term storage, meaning control over salt equated to control over survival itself. And near Solnitsata lies the Varna necropolis, dated to roughly the same period and famous for containing the oldest known worked gold in the world, with some graves holding astonishing quantities of gold artifacts far exceeding what would be expected in a small regional culture, making the connection difficult to ignore. One plausible theory is that Solnitsata functioned as a primary economic engine, producing salt that could be traded across vast distances, generating wealth that eventually accumulated in places like Varna, suggesting that gold may not have been the origin of wealth, but rather its consequence. And if this interpretation holds true, Solnitsata could represent one of the earliest examples of a resource-driven economy, predating formal currency systems by millennia. The presence of massive stone walls introduces another layer of mystery, as fortifications of this scale are rare in settlements of this age, especially those with relatively small populations, raising the question of why a salt production site would require such heavy defense. With the most obvious answer being value, since if salt was as important as evidence suggests, Solnitsata would have been a strategic target. Yet the scale of defense implies either constant threat or exceptional importance beyond simple resource protection. When compared to early fortified sites like Jericho, which also built defensive walls but within the context of large, permanent populations, Solnitsata stands apart as a specialized hub rather than a sprawling urban center, suggesting it was defended not because it was large, but because it was critical. By the end of the 5th millennium BCE, Solnitsata was abandoned, and there is no clear evidence of destruction, no widespread burn layers, and no mass graves indicating violent conflict. As production ceases, occupation ends, and the system dissolves, leaving only unanswered questions about whether environmental changes, such as shifts in groundwater, salinity, or climate conditions affecting evaporation, may have played a role, or whether the trade networks that sustained the settlement collapsed, rendering the entire operation obsolete. But despite these possibilities, there are no definitive answers, only the silence left behind by a system that once functioned with remarkable precision. If a system this advanced could exist so early in human history, what do you think we've lost that we still haven't rediscovered? Share your thoughts in the comments below. buried beneath a low, unremarkable mound in northeastern Bulgaria, a chamber carved more than 2,000 years ago challenges one of the oldest assumptions in archaeology, that tombs are built for the dead. Inside the Sveshtari tomb, 10 sculpted women appear to float along the walls, their bodies curved in unnatural poses, their arms raised not to support the ceiling in any structural sense, but as if lifting something invisible upward. The geometry is precise, the symbolism deliberate, and yet the function remains unclear, creating a contradiction that has persisted since its discovery. This is not simply a burial chamber, but a system designed with intent beyond death itself. The tomb was discovered in 1982 during archaeological excavations in the Sporianovo Archaeological Reserve, a vast landscape containing more than 100 Thracian burial mounds, most of which follow predictable architectural patterns involving simple corridors and modest chambers. At first glance, the mound concealing Sveshtari appeared indistinguishable from the others, rounded, silent, and untouched for over 2 millennia. But as excavation progressed, researchers uncovered a far more complex structure composed of a long dromos leading into sequential chambers and culminating in a central vaulted space of unusual proportions. What immediately distinguished this chamber was not just its layout, but the presence of 10 caryatid figures arranged with striking regularity, a feature completely unprecedented in Thracian archaeology, suggesting either external influence or a localized tradition that has otherwise vanished from the historical record. Initial structural mapping revealed that the chamber was not constructed randomly, but followed a consistent geometric logic, with the curvature of the vault, the spacing between sculptural elements, and the alignment of decorative motifs all adhering to proportional relationships that imply deliberate planning rather than intuitive construction. However, this precision was not accompanied by any evidence of advanced measuring systems, such as calibrated tools, marked grids, or metal frameworks, raising immediate questions about how such accuracy was achieved. As excavation continued into detailed artistic analysis, archaeologists observed that the 10 caryatids shared nearly identical proportions, each carved to a consistent height and positioned symmetrically along the walls. While subtle differences in posture created the illusion of movement, an artistic sophistication rarely associated with Thracian craftsmanship. When compared to Greek caryatids, such as those of the Erechtheion, which visibly support structural loads, the figures at Sveshtari appear detached from functional necessity, reinforcing the idea that their purpose is symbolic rather than architectural. Further contextual analysis complicated the picture even more, as the tomb yielded surprisingly few artifacts relative to its scale. Unlike Egyptian or Macedonian royal burials, where inscriptions, regalia, and grave goods clearly establish identity and status, Sveshtari provided no definitive inscription and only limited material evidence, leaving the identity of its occupant uncertain and suggesting that the structure's purpose may not have been centered on burial in the conventional sense. At the heart of the Sveshtari tomb lies a technological contradiction that challenges established assumptions about Thracian capabilities, as the culture is not historically associated with the kind of advanced stoneworking seen in Egyptian or classical Greek architecture, where precise geometry and refined carving techniques are well documented. And yet, within this chamber, the ceiling features a rosette motif executed with near-perfect radial symmetry. The spacing between the 10 caryatids follows consistent intervals, suggesting controlled measurement, and the curvature of the vaulted ceiling distributes weight evenly, despite the absence of visible reinforcement or structural redundancy. In experimental archaeology, attempts to replicate such symmetry in limestone using only primitive tools typically result in measurable deviations, often in the range of 1 to 2 millimeters per segment, which accumulate across circular designs and produce visible distortions. However, in Sveshtari, such distortions are almost entirely absent, indicating a level of precision that implies either highly refined techniques or a method of measurement that has not been preserved. When compared to other Thracian tombs, which generally exhibit less geometric control and simpler decorative schemes, Sveshtari stands as an anomaly, while comparisons to Greek and Macedonian structures raise further questions, as those cultures possessed well-documented toolkits and engineering traditions that the Thracians did not clearly share. Several explanations have been proposed, including the possibility of imported knowledge from Hellenistic artisans, the existence of lost local techniques developed over generations, or the prioritization of symbolic precision over structural necessity. But none fully account for the consistency observed across multiple architectural and decorative elements within the chamber, suggesting that what is present here is not isolated craftsmanship, but a coherent system of precision embedded within the design itself. Among the most compelling elements of the tomb is a relief depicting a mounted figure, often interpreted as a Thracian ruler or hero, surrounded by symbolic forms that suggest elevation rather than burial, a depiction that diverges significantly from traditional funerary imagery focused on interment or mourning. This scene, combined with the upward gestures of the 10 female figures, reinforces a thematic emphasis on ascent and transformation, aligning with certain interpretations of Thracian belief systems, in which death is not viewed as an endpoint, but as a transition to a higher state of existence. In this context, the architecture of the tomb can be understood not merely as a container for the dead, but as a structured environment designed to represent or facilitate a metaphysical process, where spatial arrangement, sculptural symbolism, and geometric precision collectively encode a narrative of transformation rather than finality. Despite decades of research, the identity of the individual associated with the Sveshtari tomb remains unresolved, with no inscriptions, definitive royal markers, or burial inventories sufficient to confirm ownership, an absence that stands in stark contrast to other ancient burial traditions where identity is clearly emphasized. While some scholars have suggested a connection to the Thracian ruler Dromicates, who lived in the 3rd century BCE, the evidence remains circumstantial, and the scale of the structure appears disproportionate to the limited material evidence found within it. This discrepancy raises the possibility that the tomb was not constructed primarily to commemorate an individual, but to serve a broader ritual or symbolic function, in which personal identity was secondary or even irrelevant. Within the Sporionovo Reserve, more than 100 burial mounds have been documented, yet none replicate the architectural complexity or symbolic program observed in Sveshtari, creating a significant anomaly within the archaeological record. If the design reflects a broader cultural practice, its absence elsewhere is difficult to explain, while if it represents a unique experiment or localized tradition, its sophistication raises questions about why it was not repeated or further developed. Archaeology typically relies on patterns to establish cultural norms and technological progression, but in the case of Sveshtari, the lack of comparable structures leaves researchers without a framework for interpretation, reinforcing the idea that this site occupies a category of its own. So what do you think this structure really was, just an unusual tomb, or something far more advanced like a ritual system designed to transform the soul? Share your thoughts in the comments below,